Oh baby, I wanted you to be here inside my arms where the night goes down.
All right, everyone, it's 9:35, so we're going to get started. For those who have just joined, thank you again for joining us for the second day of the Nextflow Summit. We have a great lineup of talks for you today, and we're going to kick it off right now with Ankit Malhotra, who is going to talk to us about accelerating biomedical and genomics research on AWS. Thank you.
Sorry, in case you were sleeping. Morning, everyone. So, my name's Ankit. I lead genomics business development and strategy at AWS for the public sector globally. Thank you to Nextflow for organizing the summit and for giving us an opportunity to talk. I'll just give a brief overview of what and how AWS supports genomics industry, as well as research, and then sort of leave you guys with sort of a sense of where we are going as an industry, leave you with a challenge, and then later I have my colleague Kevin, who's going to talk about some practical considerations about running Nextflow on AWS. So that's going to be more interesting talk maybe. But let's first talk about genomics, right? I've been at AWS for about 4 years now. And before I joined AWS, I was a staff scientist. I've gone through the rigor of being a grad student, postdoc, and then being in the genomic space for over 20 years now. I started back when in 2003, right after the publishing of the human genome, the first publish. And we got a great talk about this from Adam yesterday about the evolution of the whole human genome and the attempts to sequence it. The promise that I started off with back in 2003, I think that promise is still there, right? But it's becoming more and more relevant these days, especially given all the transformative technologies that we have that are pushing the field with sequencing data and on the computing side, where genomics is now considered an important piece of the puzzle when you think about impact on research and population health. Especially coming out of the pandemic, where the sequencing of the viral genome and development of therapeutics against it, the vaccines against it, was critical to us being able to respond to it. Genomics is increasingly being used to understand disease, for therapeutics, for diagnostics, understanding prevalence of disease, and understanding how population evolves, the structure of the population. And this is all being driven primarily because of the access to genomic data. Back when I started, this is a graph. I think the data is readily available on NIH's website. Back when I started, right after the human genome was published, we estimated that you can do a human genome for about $100,000. I'll come to that slide. And then over the last 20 years, we have seen this dramatic 3 orders of magnitude decrease in the cost of whole human genome sequencing, down to where Illumina, as of last year, I think, said you can do a 30x short reads whole human genomes for about $200. And we are finally getting to that stage where you're going to see this inflection point where genomics is starting to get applied not only on the research side, but also in healthcare settings. And that's where I think we'll see this challenge, the challenge that we have in genomics of data, compute, just explode. This is just a short list of various initiatives, consortiums, biobank projects that are going on across the world today that are trying to use genomics in a population setting. This is all across the world. I think this is only about 36. I'm sure I've missed some. T2T and the Pan-Genome Project didn't make it up there. But this gives you an idea of how quickly, given the reduction in cost, how quickly population health programs are starting to think about adding genomics as their one of the data sets that they use. To the extent that in the next 10 years, we are estimating that graphic that you saw is just going to expand, it's going to grow. We'll see somewhere close to about 200 plus global initiatives start to use genomics for population health, for research, and increasingly for clinical use cases. And over 100 million individuals will have some aspect of their genome sequenced in the next 10 years. I think there was an estimate last year with a report that said somewhere close to 28 million people have already had some level of their genomes interrogated, whether it's panel sequencing, whether it's whole human genomes, whether it's exomes or something, right? I think that's going to grow. And this is probably an underestimate. This is 100 million individuals just looking at the growth trajectory that we have. But if the costs continue to come down and genomics starts to get picked up more for clinical genomics, more for the healthcare aspect, that number is going to explode. And assuming, I mean, this is our previous estimate, right? Assuming one person's genome takes about 100 gigabytes of storage, 100 million individuals, that's 10 zettabytes. Who's going to store that? Do we need to store that? Who's going to process it? How do we process it? This is going to be a big challenge. And this is all to enable this flywheel. I come from a research background. I've mostly focused on the right-hand side of this particular flywheel, which is how do we push the boundaries from a research perspective. You look at scientific literature, you look at real-world evidence, you form your hypotheses, you apply those hypotheses, do biomarker discovery, find targets, identify targets for drugs. But then eventually, I think we are going to that, starting to do more and more of this entire flywheel, where these insights are now getting pushed back into healthcare. And we're starting to see precision diagnostics. We're starting to see clinical decision support systems and personalized care coming out of it. And this flywheel is going to accelerate the adoption and making this challenge even bigger. What we're also starting to understand is while genomics is great and genomics has a lot of potential, it's not everything. It's probably one leg of a multi-legged approach that we need to take if you're thinking about doing precision healthcare, precision medicine. So the entire industry, I think, in some aspect or the other, is starting to move from doing genomics to doing multi-omics to doing multimodal analysis for research in healthcare. Individuals today, I mean, most of us have smartwatches on. We have incredible amounts of data that we are collecting. And every encounter that you have with smart devices, with going to your doctor's office, you're generating data that's important that we need to understand if we need to push the boundaries on what is precision medicine. So individuals today walk around with thousands of data points being collected. And what we need to start to do is we need to start to look at a more holistic view of an individual. Genomics, as I said, is important. It sets the baseline. It also lets us track how the stuff is developing within an individual from a genetics point of view, but it's one aspect. And more, what we are starting to see is organizations starting to collect imaging data, collect clinical encounters, social, geographic data, data from devices and instruments, and start to bring all of these things together. And this is where I think there's still the need for a lot of method development, a lot of algorithm development, approaches for how do you even start to bring these disparate data sets that never have been integrated before. How do you standardize them? How do you harmonize them? And then increasingly, how do you start to apply AI ML approaches? Because Gen AI is the big buzzword these days. But I think that's where a lot of innovation still needs to happen. Are large language models really what is needed, or do you need other approaches from an AI/ML perspective, but enabling multi-omics and multimodal analysis where you start to bring together clinical records, omics data from an individual, imaging data, collecting it, harmonizing it, normalizing it, and then making it integrated so that now you can start to run AI/ML models on top of it to generate insights. I think that's the story that the entire industry is sort of moving towards. And so that's sort of our, from an AWS perspective, that's the thesis that we have on how we are sort of investing to help in the research and the healthcare industry. We have been, so AWS works, the way that we develop stuff is through a working backwards philosophy. So the way that works is we see trends in the industry, then we go to the people who are doing this on a day-to-day basis and try to understand what are their pain points. And then we try to solve for those pain points in that working backwards fashion to come up with those solutions that will move the field forward. So in the last couple of years, we have started to develop purpose-built services, especially for the healthcare and the research industry. Things like AWS Health Lake, which allows you to store health data in FHIR format, store it, transform it, transact it, and analyze it. Things like AWS Healthomics, which is a managed service that AWS put out there that allows you to store, query, analyze, and generate insights from the data. Health imaging, which is sort of the parallel service to Healthomics, but for imaging data, currently for DICOM data, but once again, to store, analyze, and share medical images. And more recently, HealthScribe, which allows you to generate, using GenAI approaches, clinical notes from patient-clinician conversations. And this is all about solving for that common denominator. If you go back to this image that I showed, how do you enable people to collect data, to harmonize data, to integrate data, so that you can finally concentrate on what's important, which is generating insights from the data. I'll give you one example. So this is Roche. I'm sure most of us have heard of it. They needed a platform to unify multimodal health data sets to fuel R&D within their organization to push the boundaries on personalized medicine. And they built their next generation infrastructure, which is called Apollo on AWS. It unifies EHR, imaging, diagnostics, wearable devices, and genomics data together to generate a better high resolution view of the individual, of the patient. And this allows them to push the boundaries from a research perspective. And more, I think this multimodal aspect of research in healthcare, we are starting to enable more use cases, more workloads. So whether it's genomics and precision medicine with AstraZeneca, I'm not sure if you guys saw, there was an announcement from the UK Biobank just today. We have there released 500,000 whole genome sequences from the UK Biobank project in their research analysis portal. That was just happened today. And then on the imaging and analysis side, applying machine learning solutions to generate insights across the industry with the Melody platform, using it for virtual screening, for connected labs and knowledge graphs. One thing that I'm very proud of is during the pandemic, Moderna, which uses AWS as their preferred cloud service provider, was able to accelerate their development of their vaccine. They went from getting the sequence back to having a clinical launch within 42 days using the AWS cloud service platform. So the central thesis on the genomic side, and I think on the multimodal side as well, is these were the challenges that we are looking to solve, right? These are the central hypotheses that led to the formation of those healthcare services. People said workflow management is hard, and we are at the Nextflow conference, so I think that's solved, right? But workflow management is hard, and it's extremely challenging to do it at scale, and I think that's one of the things that this room is very aware about. But then there's also this other challenge about integrating across the health spectrum of various data sets. Collaborating on a global scale, I think there's efforts, and I gave you one aspect of it with those global initiatives on the map, but collaborating on a global scale is still a challenge. We are still very siloed in our approaches, and I think that's something that needs to be solved while adhering to the laws and around compliance and data sovereignty. And then, of course, converting data into strategic assets that can then be used across the spectrum is the other challenge. So taking a step back, how does AWS help with research? It primarily starts off with realizing that from a scientist, from a researcher perspective, you don't want to be worrying about servers. You want to be worrying about science. So the AWS Cloud Service Platform allows you to do that. It gives you the access to a wide variety of compute instance types, storage types, so that you use the cloud when you have the need, and then the cloud goes away. And then with projects like the UK Biobank, with projects like the stuff that we're doing with Baylor, the stuff that we're doing with the Allen Institute, initiating, fostering collaboration across organizations, giving you access to data sets that are from other institutions through the Open Data Program, allowing you to leverage and share the effort across various sites where you can containerize workflows and share them. Once again, in this room, I think we're all aware of how reproducibility has always been a challenge in science, and especially in bioinformatics. And that's where I think stuff like workflow orchestration languages and containerization sort of helps to solve the challenge of reproducibility. And then making available the state-of-the-art AI and machine learning tooling so that people can start to focus more on generating insights from the data, all the while built on what is job zero at AWS, which is security. Just to give you a sense of the various different instance types and the workloads that are supported with Amazon EC2, the compute platform at AWS, we have, I think, close to over 100 instance types that support all different kinds of HPC workloads, whether they are HPC optimized, whether they're optimized for compute, whether they're optimized for storage or memory or networking. And then specialized instance types with instances that have the latest state-of-the-art GPUs, or that are specialized for machine learning training, machine learning inference, F1s that allow you to use FPGAs to accelerate genomic analysis. It provides you that flexibility and that scalability that you need when you're trying to push the edge on algorithm development, and then the scalability when you have to put this in production. I'll just give you 3 examples of HPC optimized EC2 instances with the EC2 HPC 6A, which is optimized for basically a lot of different cores with a lot of memory, and being used for compute-intensive applications like CFD and numerical weather prediction, or these EC2 HPC 6ID instances, which have about a terabyte, I think, of RAM, and are being used for those memory-bounded data-intensive workloads. And then the Graviton instances, which are basically our own silicon that we can give you the price performance benefit back that provides low latency, high network performance with the HPC 7G. So there's multiple layers at which AWS allows for enabling HPC workloads in the cloud, right? Starting off with compute and networking, we already talked about EC2 and the networking adapter, but then also how you spin up clusters with AWS Parallel Cluster. How do you get access to fast, efficient storage with Amazon FSx for Lustre? How do you do batch processing? And I think a lot of people in this audience are either using or should use AWS Batch to automate all the workloads. And then at the end of the day, how do you do visualization with nice TCV? This wide variety and the flexibility of instance types gives you that ability to do cost-effective analysis, right? So this is one particular example where we took, working with Sentient, we took their FASTQ to VCF pipeline and just benchmarked it across all the different various instance types that we can think about, and to process short-read data, 30x short-read data from Illumina for one whole human genome. And I think the best performance that you got was out of the HPC6A Graviton instance, where this 30x whole human genome went through the entire pipeline FASTQ to VCF in under 32 minutes with about $1.50 in on-demand costs. And this blog is readily available if you just search for Sentient on AWS benchmark. But we have similar benchmarks for Parabricks and other solution providers, even with GATK. So that's just an example of how we are supporting at a very high level research and biomedical research in healthcare. Just to give you a few examples on some success stories. This is a particularly recent one, working with the Wisconsin Public Health Labs, Dr. Kelsey Florek over there. They had built this Nextflow algorithm, Nextflow tool, that they were using at Wisconsin to do some viral surveillance-related work at that public health lab. But then there was a need on how do you get other public health labs across the country to adopt this, right? They had already been using Nextflow, but Wisconsin was fortunate in having Dr. Kelsey Florek over there who could run these workloads. Not all public health labs have bioinformaticians within their staff, so the challenge was, how do you make this easy? How do you make this simpler that multiple folks without bioinformatics training can run these important workloads? And so through a collaboration between us and a development partner out of Australia called Two Bulls, we built a solution on top of Nextflow Tower called Easy Genomics that leverages those Tower APIs to, in a simple fashion, in a simple dashboard, allows you to move the data from the sequencers into the cloud and then run Nextflow pipelines on top of it without needing to be a bioinformatician, without having that skill level in there. So it allows you to securely log in to the platform, upload data sets, select the appropriate analytic workflow, which is written in Nextflow, monitor the sample progress using the Nextflow Tower APIs, and receive the results through within the browser or through emails. Another example is the work that's done with the Chan Zuckerberg initiative. This is more of a community effort. It's called the Open Challenge, Open Problems in Single Cell Analysis. So single cell analysis, as most of us are aware, is not a solved problem. There's still a lot of algorithm development that needs to happen. So they built this portal which allows for them to basically put challenges out there for the community to solve, get their workflows, and then run that against the benchmark data and get results out of it that can be then compared, all with a sense of driving innovation in this field. And all of this runs on AWS. So I think running out of time. I also want to leave you with some research programs and initiatives on how we support people getting started on AWS. One of the first ones I want to talk about is our Registry of Open Data, which is a set of genomics and other life sciences data sets that we host for the community for free. So if you ever had the need to basically run against TCGA, against the Kids First data sets, against Nomad or anything, or data from the Sequence Read Archive with the NIH, all of that is hosted on AWS for free for people to use. There's also something called there's an application program. So if you have a data set that you think is a community resource and should be hosted in the cloud, do apply for that particular program, and we'll work with you to basically get that uploaded and made available for the research community to use. And this is part of our AWS Data Exchange. Data Exchange is sort of that marketplace for data. It's a managed service that enables AWS users to find, subscribe, and use third-party data in the cloud. Now, the data in the registry of open data, that's hosted for free, so there's no charge within Data Exchange to use that data. But if you have a data set that you think is an asset and you want to give access to users, but then be able to subscribe in some kind of a financial model, then the Data Exchange also allows you to basically make that available in a secure fashion. The second program I want to talk about is the AWS Cloud Credit for Research. This is something that's existed for multiple years now, but I feel like not many people still know about it. It basically provides cloud credits for researchers, students, postdocs, faculty. When you're thinking about a research project, a proof of concept, and you want to get started in the cloud, you just apply for this particular program. You describe what you're looking to do, and provide an estimate of the amount of resources that you need to get started. Then it goes through a review process where it's people like myself, subject matter experts in the field, who understand, who look through the applications and basically approve them. And you get basically credits to get started in the cloud. You also get consultation through our subject matter experts for helping you get started. And then I'm promised this is the last slide, and then you go to questions. But we also launched something called the Health Equity Initiative. This is a program. I think we are going into the third year of the program. So it started at the height of the pandemic, and the idea was, how do we support critical healthcare research that improves the equity that in the healthcare field. I think yesterday Adam gave a good example of how there is a lot of bias if utilizing HG38 only for their baseline analyses, and how that move to the pan-genome with having data sets from multiple ethnicities, multiple population groups, will help solve this gap in equity. I think that's a perfect example of a use case that would and should be supported through the Health Equity Initiative. So we're basically looking for project ideas. We are basically looking for proposals from the community for projects that will increase access to health services, reduce disparities by addressing the social determinants of health, or generating those data sets that fill in the gap that exists out there, especially in genomics, to promote equitable and inclusive healthcare. So this goes through a cyclical application process. There are 3 application deadlines throughout the year. It's a global program, and I think the next application deadline is in March 31st of 2024. So if you have an idea, if you have a proposal that you think helps address the gap that we have in the field, definitely do look at it. This comes with not only AWS credits, but also we can support through our professional services for helping you get started on this particular important topic. And yeah, I'll stop with that. I think I'm right around at time. Thank you very much for listening, and thank you for the opportunity.
Thank you, Ankit, for this very comprehensive overview of AWS services. We'll hear more about Nextflow on AWS in about 15 minutes. But for now, thank you very much.
Thank you.
I would like to call Stephen to the stage, who is going to talk to us. About neoantigen. And while they're setting that up, I want to remind you, please post any questions you might have for the speakers in the Slack channel. Yes, please comments, questions, anything like that in Slack, and then we'll ask the questions after that. Thank you.
Perfect. Okay. Thank you for the opportunity to speak today about my work. My name is Steve Vinsko, and today I'm going to be discussing enabling reproducible and flexible neoantigen prediction with Nextflow. First, a bit of background about myself. So I started with Nextflow in late 2019 when I joined the Vincent Lab at the University of North Carolina at Chapel Hill. The vast majority of my experience has been with the DSL2 syntax. My focus has been on two primary pieces of software, Raft and Lens, which I'll be presenting today, and I try to contribute where I can. Here's a blog post I published late last year, where I provide a tutorial and demonstration for implementing Stephen Ficklin's solution for minimizing the storage impact of large intermediate files, which I know is kind of an issue with Nextflow. Within the lab, we focus on personalized neoantigen vaccines. So neoantigens in this case are defined as tumor-specific antigens presented by MHC molecules on the tumor cell surface. So the hope is that T cells from a patient's immune system will recognize these antigens as being non-self, and that will trigger an anti-tumor immune response. To predict neoantigens, we typically take healthy cells and tumor cells from a patient, we sequence them, we then run them through a workflow, and the workflow provides us with antigens along with metrics around them so we can help rank and prioritize them. These antigens, or neoantigens, can come from single nucleotide variants, somatic insertions, deletions, and somatic gene fusions. So if you want to predict neoantigens, there's a variety of workflows currently available. By my count, there's at least 26 publicly available workflows. So why make another one? So immuno-oncology is a field of hard, unsolved questions, and most current personalized vaccines show very little success. There was a bake-off in 2020 where they had 25 different research teams predict neoantigens for a set of samples. And the organizers then went through and tested these in the lab to see which were immunogenic, which of these peptides could actually stimulate the immune system. And what they found is that only 6% of them were effective, which is obviously bad. This is highlighted in a recent review where the author points out the fact that most pathogen-specific vaccines, such as for yellow fever, result in robust and lifelong immunity, while most neoantigen vaccines result in effectively no clinical benefit for the patient. So even once we address the issue of immunogenicity, there's still other hard, outstanding questions. So remember, tumors have heterogeneity, they're complex. So once we understand immunogenicity, can we then predict how tumors are going to respond to treatment? And assuming we can predict how they're going to respond to treatment, can we then develop strategies to counter any sort of evasion mechanisms they use so we can ensure full elimination of the tumor? Beyond that, a lot of the current workflows that are available have shortcomings. For example, they're rigid. This is an issue because many of the tools in the field generally have suboptimal performance. So here we're looking at NetMHCPan, which is a tool used for predicting the binding affinity between an MHC molecule on the cell surface and the peptide it's presenting. And we're comparing that to TR-FRET data, which is empirical binding affinity data. And so what you can see here is that across these three class 1 HLA loci and the alleles within them, the percent agreement between the computational prediction and reality is terrible. And so having the ability to switch tools for other tools or upgrade tools to newer versions would be very beneficial for our workflow to be applicable to the field or more utilizable to the field. Beyond that, a lot of the current workflows support limited antigen sources. A lot of them focus on somatic single nucleotide variants, somatic insertions, deletions, and somatic gene fusions. But recent work has shown that other sources, such as endogenous retroviruses, are also worthy of consideration. They also support limited technologies. A lot of these workflows assume that you have short-read whole gene or whole exome data along with short-read RNA sequencing data. However, we know that short-read and long-read, single-cell and long-read sequencing is becoming more affordable and more available. So having a workflow that can adapt to these new technologies as they become more mainstream is highly beneficial. And finally, a lot of the workflows aren't well maintained. The last time I checked, the average time since the last public push for these workflows is around 600 days, so a little under 2 years. So of course, the solution to all of this is Nextflow. And so to support our neoantigen workflow, we developed a tool called Raft, which stands for Reproducible Analyses Framework and Tools. We started this back in 2019. It's effectively a Python 3 wrapper around Nextflow DSL2, and we had a couple of development goals with Raft to support our purpose in the lab. The first one is a project context. And so what I mean by that is effectively a template that can house an end-to-end analysis. This includes the inputs, the FASTQs, references, metadata, manifest, whatever, along with all of the Nextflow modules utilized within the project and any code modifications made to them. So our idea here is to have effectively a turnkey end-to-end analysis that we can go back to. We also wanted broad tool and workflow support. So if you go to Raft and run the available modules command, you'll see the current list of modules we support. These are broken into tool level and theme level modules, the themes here being effectively sub-workflows that you can kind of combine together to make larger workflows. Each of these modules, of course, have their own repository on GitLab. And we also have module dependency resolution. So for example, in this case, we're loading the RNA quantification module. Raft goes through and loads all of the other modules that the RNA quantification module is dependent upon into that project. We also wanted to support off-the-shelf workflows. So we wanted people to be able to run Raft on their data without having to know the ins and outs of Raft. Currently, we only have 5 workflows, so lagging behind the 93 NF core workflows. But the idea here is that people can, with their data and a manifest, give Raft an arbitrary project name, the workflow they want to run, and their manifest. Raft will go behind the scenes, download the default references, download the modules required, hook together all the sub-workflows, and actually kick off Nextflow for the user. So more or less a one command from FASTQs to results process. We also have a demo mode for the workflows. So if you don't want to be burdened with providing your own samples, for some workflows you can go through and do run demo, and it'll download, effectively do the same thing as the off-the-shelf process. However, it will use a predefined set of FASTQs and a predefined manifest, so you don't have to be required to provide one. We also wanted extreme modularity and extensibility. We want the ability to support new tools as they become relevant within the field. So in this particular scenario, we're using FASTP for FASTQ trimming, we're using star for the alignment of those trimmed FASTQs to reference, and we're providing star with some parameters here. So you can kind of see we're going from FASTQs to FASTP to star through the layers of the workflow. But imagine you have a colleague who hates FASTP and star and instead wants to use trim galore and BBmap for whatever reason. In that case, you can simply go to the configuration file, change the configuration file to the tools you want to use, assuming they're supported, and the next time you run that workflow, you actually go through a different path to that workflow and still you'll get to your outcome, but through a different set of tools. And finally, and perhaps most importantly, we wanted project-level reproducibility. So I mentioned the idea earlier that projects are effectively self-contained end-to-end analyses. And because of that, we can produce what's called a Raft package. This is essentially a tar file that includes a minimal yet sufficient amount of metadata from a project to reproduce it later, not only on the same computer, but in a completely different environment. This includes the checksums of the inputs, outputs, references, et cetera, the modules used within that project, and any modifications the user made to those modules, an auto.raft file, which is effectively a history of how the user put together the project, and optionally a metadata file that includes patient-level information. We made this optional because you don't want people including potentially sensitive clinical information and pushing it out there to the public. But the idea is that once you create this Raft package for your project, you can then share that 10 to 50 meg file with a colleague, and assuming they have the same appropriate references and input FASTQ files, reproduce your end-to-end analysis in their own environment. So we actually developed all of this to support LENS, which is our neoantigen workflow, which stands for Landscape of Effective Neoantigen Software. It looks similar to the plot you saw in Figure 2, but in this case, it also shows what we can actually define here with respect to tumor antigens. So we look at SNVs and indels, fusions, similar to the other ones. We also look at splice variants, cancer testis antigens, self-antigens, viruses, and endogenous retroviruses. So for all these tumor antigens, we go through and we provide information regarding the binding affinity and the binding stability and the relative abundance, among other things, which can help you then go through and prioritize your antigens. And when you run LENS, you'll get plots like this that you can kind of use for QCing and seeing what you found within your samples. And again, you also get a report that has all the other information you would need to prioritize your targets. Within the lab, we've had a graduate student use LENS within their project, their PhD thesis. And so Misha ran LENS on BBN963, which is a bladder cancer mouse model. She ran it on 3 separate replicates and then took the intersection of the targets among those replicates. She then ran this on an ELISpot, which is a molecular assay for determining immunogenicity within the lab. And we had success. Roughly 10% of the peptides that she tested were positive for immunogenicity. You can kind of see the LE spot here in the lower right, along with the actual readings in the upper left. So it's a minor success, but I'm going to count it as a success. We are also working towards moving Lens into the clinic. So we have a clinical trial at UNC called PandaVac, which stands for Personalized and Adaptable Vaccine. We're currently focusing on non-small cell lung cancer and head and neck cancer, and we're only focusing at the time on somatic single nucleotide variants and somatic insertions and deletions. The reason why we're looking at just those particular targets and not the other ones I mentioned is because with these, we can observe them in DNA with the variant calling and then confirm them and quantify them in RNA. So we have more confidence that they're actually real. And when you're dealing with patients, obviously you want to be highly confident in what you're doing. The future of Lens is quite bright. So we have several groups within the lab working on projects that will enhance Lens in the future. We have Alex and Andy working on long-read neoantigen detection and quantification. We have Duvy working on machine learning-based modeling of PMHC-TCR interactions. We have Julia working on machine learning-based analysis of mass spec data. We have Dan working on analysis of single-cell data to help us better understand tumor heterogeneity. We have the rest of the lab that are doing all the wet lab work to actually confirm these things. And last but not least, we have Brian Parker, who's helping with the user experience of both Raft and Lens, and also helping a lot with the internals of Raft and Lens. And with that, I'll take any questions.
Thank you so much for the great talk. Did you notice a performance penalty by wrapping Nextflow in Python versus a native Nextflow?
No, so we're actually using native Nextflow, right? So Raft is really doing all the busy footwork before you run Nextflow. It's setting up the project, it's loading the references, it's doing all that stuff, so that when you run Nextflow, we're actually running Nextflow with a pretty augmented long command that's pointing Nextflow to all the Raft stuff that it's doing. So you're still running raw Nextflow at the end of the day. You can still take, actually when you run Raft, it gives you the literal Nextflow command it's running, and you can copy and paste that and run that just as it is without having to use Raft. But again, Raft is kind of helping get that project set up and doing all the footwork.
That's very cool. Thank you very much.
Thank you.
All right, next we have Kevin Sayers is going to talk to us about Nextflow, options for using Nextflow on AWS.
Good morning, everyone. My name is Kevin Sayers. I'm a research scientist at AWS. I'm part of our professional services team, so I work with customers, including those customers who are bringing Nextflow to AWS. And so what I want to do today is go over some different choices and considerations if you were to be bringing your workflows to AWS, and kind of as you assess how you want to run your workflow. And so the main question I want to do is basically look at, if you were a user coming to AWS, you have your Nextflow workflow, how do you run on AWS? There's a variety of services. Are there better ways to run it than others? And so also to frame this, I want to go over a couple of key considerations. Look at each of those different services. There are things like expertise, where especially the different orchestrators or resource schedulers, having that existing expertise is something you want to weigh as you're kind of evaluating the different services. Likewise, different workloads. Are you bringing just a set of Nextflow workflows, or are you bringing basically all of an HPC to AWS and you have a variety of different workflows? Next, one of the considerations is the configuration. And this is both the Nextflow configuration that enables you to work with the different services, as well as the actual configuration available to you within those services. So things like different EC2 instances or storage that might be available depending on the service you're using. And then finally, the integration with the larger set of AWS services, if you want to plug it into some other sort of business logic to accomplish your workflow needs. And so again, these are just kind of some of the things to keep in mind as you're looking at the different services, and I'll try to highlight, as with the specific services, some of the areas from these that kind of stand out for a given service. So the three services I want to talk about today are basically those that enable you to create your own cluster in AWS and run Nextflow. And so we'll be looking at AWS Batch, which is probably the one most people in this room are familiar with. But it's a fully managed batch processing service. Also AWS Parallel Cluster. And this is a way to create a Slurm cluster on top of EC2 instances and have that very traditional HPC environment. And then finally, Amazon EKS, which is our managed Kubernetes offering. And so first what I want to do, and this might be very familiar to everyone, but kind of step through what a somewhat generic workflow analysis on Nextflow looks like in terms of the architectures, and then also highlight some of the different key components. And here I'm using batch kind of as an exemplar, but the key bits are actually shared between parallel cluster and EKS as well. And so kind of walking through this, initially you have a user who has a Nextflow file as well as a config file, and this is setting basically the executor for a given service. So again, here this is just using batch as an exemplar. Then that AWS service is going to take in the jobs that are specified in the processes in the Nextflow workflow, and basically send this into a compute environment. And so this compute environment is then the EC2 instances, and so you have a full menu of different EC2 instances that you can plug into your compute environment and get different accelerators or optimized instances for things like compute and memory or HPC. Then the other piece of this is, of course, that you need some way to pull in your tools, and obviously Nextflow supports a variety. I've got Conda, containers, et cetera. So here just using an example of pulling in a container. So this pulls into the compute environment and is run on top of those EC2 instances. And then the last piece of the puzzle is then having some storage. So here just using S3, both for like the work directory as well as the inputs and outputs and whatnot. And so again, this is using batch as an exemplar, but the key things here, also shared by parallel cluster as well as EKS, is basically that you have some EC2 compute, you have a variety of different storage options, and then you have ways to host and manage the tools you're using, all behind an AWS service that Nextflow can then be configured to use. So stepping through the services individually, I just want to do some highlights as well as a bit of the Nextflow configuration that might differ between them. So for those of you who are not familiar with AWS Batch, it's a fully managed job schedule and resource orchestration. So if you're familiar with like an HPC scheduler, this is basically a fully managed version of that in AWS. And with minimal configuration, you have a fully specialized batch scheduler available to you that you can then configure Nextflow to run jobs on. It's highly integrated with other AWS services. And then you have quite a lot of flexibility in terms of setting up different queues and EC2 instances in your compute environments to leverage all of that for your workflows and kind of fine-tune it for you. And this one is probably the one most people are most familiar with. I think it's one of the oldest managed services supported by Nextflow. And then also it's widely documented both from AWS, Nextflow, Seqera, and like community blogs. So this one's very widely used. The next service, which is actually a tool, is AWS Parallel Cluster. And so this is an open source tool that enables you to create a Slurm cluster on top of EC2 instances. And so here you have it takes in a YAML file. And so in tens of lines of YAML, you're able to define the different instance types you need, the different storage you might use, and then within a matter of minutes to tens of minutes, you're able to deploy a full HPC cluster on top of EC2. And so one of the key advantages here is that it's that very traditional HPC setup. You have like a login node, you log in, you have srun, sbatch available to you. And going back to kind of those key considerations I mentioned at the start, this one particularly can enable if you have like very heterogeneous workloads. So perhaps you have some Nextflow workflows, you have some other HPC workflows, such as like molecular dynamics or whatnot. You're able to provide that very familiar environment to researchers on AWS and enable kind of the variety of different workflows that they could use. And one of the other things here to call out as well is that Parallel Cluster has a bit more flexibility in terms of the different tool dependencies. So whereas Batch and EKS are primarily container focused, this one you can use Conda, SPAC modules, local installs and whatnot. And so you have a bit more flexibility in terms of how you're managing the software you're running in your workflow. So the next service is then the Amazon EKS, and this is the managed Kubernetes service. It has a number of advantages. First off, you have some redundancy in terms of the control plane. And so you have some redundancy, and it's all managed by AWS. And you also have the ability to use the managed node groups from EKS. And so here you're able to change out instances in your node groups fairly quickly, and it's a fairly straightforward process. And so again, this allows you to have that fine-tuning capability as you're looking at your workflows to kind of swap out the instances as you needed to address the resource requirements. And then one of the big things, similar to how in Slurm you're considering additional workloads, those might be HPC. Here in Kubernetes, you can also look at other workloads that might be also supported here. And so there's a number of different data science tools and stuff that run on top of Kubernetes. And so this is another consideration. As you're looking at it, there are potentially other services that you're using that could also then be hosted in Kubernetes beside your Nextflow execution. So the next thing I want to mention, kind of looking back at the services, so batch is heavily container focused, EKS is heavily container focused, and then parallel cluster also enables the use of containers within Slurm. And so one of the services we have is Amazon ECR, and this is our managed container registry. And so this is another piece of the puzzle, kind of going back to that original exemplar workflow run, that you can also have this in your Amazon account, and then there's some benefits to hosting your containers in ECR, and then pulling into batch and EKS in your Amazon account. And the other thing I wanted to mention here was that the ECR also now has all of biocontainers in it as of last year. So again, a common community resource is also available to you in ECR to use as well. So looking back at the initial considerations, and of course this was a very quick overview just to kind of give you that first taste of the different services. But looking back at the considerations we talked about, so expertise here is obviously an important one. If you have users that are already familiar with Slurm or Kubernetes, kind of enabling them to have that similar environment, but in AWS obviously has a lot of value and kind of is less disruptive to that time to science compared to dropping them in a totally new environment. Additionally, in terms of expertise, some of the other things we talked about were the instances and storage. So, expertise in managing specific storage types can also be considered. And then looking at the different workloads is also important. Again, it kind of differs a bit if you're looking at just pulling in a handful of Nextflow workflows versus, basically an entire HPC system of workloads into AWS. And so that's a big thing to consider then, going back to kind of the parallel cluster and EKS in particular. If you have something that requires Kubernetes, maybe it's a visualization service, or if you have different HPC workloads, again, that require tightly coupled processing, that's all something to weigh as well as you're kind of comparing the services further. The next bit is to also look at the configuration. And again, we didn't kind of really dive into that too deeply in this presentation, but there are slight differences in terms of the EC2 instance types that are supported by the different services, different storage classes that can be used with the different services. And so that's also something to investigate as you're kind of doing your search and how you want to run your workflows in Nextflow, taking that kind of holistic view and understanding what the different services support and which different features you might be able to leverage to run your workflows. And the final one, we also didn't really touch on this either, is the integrations. And so this is really the ability to connect up one of these services to other AWS services. So you can think of this basically if you had an S3 bucket and you wanted to react to as data is being put into the S3 bucket, have some trigger, how can you connect it up to other AWS services that can respond to that trigger? And so again, this differs slightly between the services. Some are very fully integrated, some require a couple additional steps to get that type of integration. And so what I wanted to do in conclusion is basically, again, this was a very quick high-level overview, didn't dive too deep into anything, but at least now hopefully you have some context if you were to say, I have my Nextflow workflow, how do I run on AWS? And so we have basically a number of different services that have different features and can support different use cases and different expertise. And so we have kind of a variety of different options for you to consider as you're bringing workload. And then the other portion is kind of going to what Ankit was also saying in his presentation. The key components within the different services, we have a wide menu of things like EC2 instances, everything from HPC optimized to compute optimized. We have x86, we have ARM, we have a new ARM processor that was also announced earlier this week. And likewise, a variety of different storage options to meet your kind of workflow requirements and different portions of that. And finally, we have the ability to host the containers so you can have all your tools pulled in. And so just kind of, and as an overall conclusion, basically there are a lot of options and you can kind of find what works best for you and really fine tune both how you're running your workflows as well as the infrastructure you're running those workflows on top of. And so yeah, hopefully that just gives you, if you had not looked at AWS before, hopefully that gives you a bit of a roadmap of some things to look at. And with that, thank you everyone. Thank you for the organizers, and I'm happy to take questions now if there's time, or stop me anytime.
Yeah, we can take a couple of questions real quick. Thank you very much. Are there any generic batch Nextflow infrastructure plans out there, like Terraform, for example?
So we have some workshops to provide. I don't know if we have a Terraform specific one, but there are workshops out there that have kind of a blueprint for doing it. And then of course there are also a number of like community ones as well as like blog posts from Seqera that kind of outline what you would do.
Very well, thank you. Are there any guidelines on how to configure split cost allocation reporting so that we can more easily track costs associated with specific Nextflow jobs running on AWS batch?
So there has been, this is maybe perhaps a little too much to dive into right now, but there are different tools that have been released over the past year that give you more fine-grained control of monitoring of both the costs and resource utilizations of batch. So there are different options out there. So I'm definitely happy to dive into that further if you stop me or reach out. So we are kind of constantly evolving how we can track that, both the resources and costs. So we have some solutions.
Wonderful. There's a few other questions, but we're out of time, so I encourage you to seek out Kevin at the coffee break, and if you can join Slack to engage in the conversation, that'd be wonderful. Thank you so much. All right, and now last talk of this session, Sam Mino is going to talk to us about the Seqera platform.
Thank you so much. I want to thank the organizers very much for giving me a chance to speak to you all today, and thank you all for your attention as we round out this session of this amazing conference. I am really excited to have a chance to talk to you today, not about anything really getting specific into the weeds on any specific workflow or architecture or bit of code examples, but instead I want to zoom out, and I want to tell you a little bit about our experience about running these workflows at our institution. And the goal of my talk is to really just give you some perspective, because at the end of this conference, you're going to go back to your institution, to your company, and you're going to be wanting to run these workflows that you love in a way that gets them into the hands of the right people, and that's what I want to share with you today. So the context that I'm working in is the Fred Hutch Cancer Center. We are a nonprofit research institute based in Seattle, Washington. We have a large number of basic research labs, over 200. We have a large number of clinical providers. There's a whole hospital that's a part of us. We also have a great centralized core facility system running genome sequencers, mass spectrometers, microscopes, pushing data out to drive all of these research activities. And it's really a massive undertaking that I've been happy to be a part of since 2017. Here's a great little photo. This is a beautiful sunset photo that you get around maybe like 3 p.m. this time of year. But it's a wonderful part of the world, and I've really fallen in love with it. And the group that I'm in has is trying to address this challenge, which is not unique to us. This is the challenge of the moment for people sort of like us, which is how do we remove any barriers to research and development and progress which are being posed by the scale, the scope, the complexity of working with this amazing data that we're able to generate. I think the talk earlier about the scale of genomics and what's going to be required to process 100 million personal genomes was really a fantastic example of that earlier today. Some of the key highlights are the cloud is amazing, but it is complex, as we just saw. The audience of the people, the different systems that need to use these resources are quite diverse. And also, there are real security and cost concerns that need to be addressed. These are extremely, extremely important to making the whole system work together well. In my specific institution, I like to think about what is the audience of people that I need to be able to satisfy the concerns of in order to be successful. And one group, that we're probably all very familiar with would be something more like the bench researcher, someone who's working in a lab. Their goal is to publish papers and get results. They're not super interested in learning everything on the command line. They need things to be straightforward. They want to be able to process their data with robust tools, be able to share effectively and move on with their life. We are also really concerned with the success of our core facilities, the people running genome sequencers, running these microscopes. They want to be able to generate the data, deliver it to users, let the users get the most out of that data, and then be able to, without disrupting the processes that they've already built up over years and years and years for making these amazing facilities run well. The third group is one that I personally identify with most. I won't ask you to raise your hands, but I suspect a number of people here would think about as being the bioinformatics staff. These are a very important part of this ecosystem. The people that are actually writing the workflows, the people that are being tasked with figuring out how to bring the data together. Anytime someone says they're doing, multimodal analysis, I think, I'm so happy for you. That sounds like a giant pain. And the people that are really tasked with making sure that we're getting the discoveries out of the analysis. And some of the challenges that I've had in that role over the years have been, how do I do something amazing and then put it in the hands of the bench scientist? How do I do something amazing and give it to my PI? How do I get data from Genomics Core effectively? And also, how do I work with my IT infrastructure? And I think that's the last group that really deserves to be mentioned. So when I think about our IT, we have an amazing centralized IT system at Fred Hutch. And I think these are people that it's easy to forget about because when they do their job well, you're not talking to them. When the trains are running on time, you're not thinking about it. And when you want to build something new, you end up having to talk to them and say, well, yes, I want this to be secure. Yes, I want to make sure that people can log in with the right credentials. Yes, I want to make sure that the right cost controls are in place. Being able to satisfy their requirements is honestly, it's a big challenge, and it's something that deserves a lot of consideration when you're thinking about the overall architecture of how workflows and analysis are running. So these are a lot of challenges, there's a lot of people. The group that I'm a part of, just by way of introduction, is actually relatively small. There's a much larger number of people at the larger organization that are a part of this. We're obviously very collaborative, and we've had a lot of great contributors. But the core team are shown here. We all come from different backgrounds. So I'm a basic scientist. I'm a microbiome. I'm a sort of metagenomics person by background. We have we have someone with expertise in cloud engineering, web development. We have an astrophysicist on the team. We have someone who's done industrial design. We all come at this from very different perspectives, which means that we all have really different ideas about how we can solve things, which has been, I think, part of the reason we've been able to come up with the ideas and the approach that we have. So when we considered the landscape we were dropped in, we considered the goal that our organization had given to our group specifically, and what we ended up deciding to move forward with was building a data platform, which is called Zero. So I'm going to talk about this. This is Zero. This is something that it's a serverless application. It's running inside our AWS. It's all AWS based, and it's all internal within Fred Hutch. But the idea is we want to have a place. We want to have a utility that can address the concerns of all the different groups that are involved in generating, analyzing, distributing, sharing, and managing these really complex data sets. When we started out this process, we wanted to keep some really core principles in mind. So the first is we want to build as little as possible. So taking advantage of managed services offered, in this case by AWS, because that was the provider we decided to go with, that was something that was really great for us because we were able to, for example, say, we're going to use HIPAA-eligible services for all the individual components. That way, we're pushing off the responsibility for managing the security of those services to someone else, and that's not in our domain of concern. It's nice to think about what you can spend time not building, right? We also wanted to keep things as simple as possible. Every time someone would build something up in the display, someone else would come down and try to rip out everything that they didn't think was necessary. We've gone back and forth. It's constantly in tension. I'm usually on the sort of the add it side of things, and other people on the team are on the rip it out side of things. So sometimes there's feelings involved. But simplicity is something that I think is really, really important for communication so that people can understand what they're looking at. A big part of this process has been listening to users. And for me, this means sitting down with scientists, not just building something and thinking, oh, it works, but instead saying, let's see what happens when I sit down next to the person who's supposed to be using it, and I watch them open up their browser, and I see where they click, and I see what they think should be happening. And to me, this is really educational. I spent my whole career in bioinformatics in the command line, and I think a bunch of things are obvious, and they're not obvious. They're like really hard to figure out sometimes, and that's purely about the attention span we all have. We all have a limited amount of time to understand things, and every additional thing you ask someone to understand is taking away from their attention budget. So you want to be able to make as little ask as you possibly can. Another big part of this for us has been collaborating on science. One of the big drivers of our effort has been picking specific scientific projects that needed a boost to be able to go further, go faster, and to be able to collaborate with those people to figure out what can we do to make this project really impactful, with the hope that what we build will then be able to provide benefits to others. So being embedded scientific collaborators is not only personally satisfying as a sort of ex-scientist myself, but also a major driver of our design decisions. So I'm gonna walk through features, and what I want to do is just 6 of them here, and I'm going to point out sort of the people that they are intended for and really why we implemented them in the context of our specific organization. And I will say, everything that I'm going to show you is very much thought of as being for a biomedical research institution. There's many different types of organizations, and I can imagine that this would look very, very different at different organizations. So the first one is data ingestion. There are a number of different places that data can come from, and we wanted to have a single place where they can land coming from different routes. So a very important one is dragging and dropping from the browser. You want a user to be able to say, hey, this data set's only 10 megabytes, why can't I just move it over? Let's make sure that can happen. People often want to be able to pull data from public repositories, so thank you NFCore Fetch NGS, big fan. Pull data from public repositories, very happy about that. People want to be able to upload from the command line. A bunch of stuff can't go through the browser, so having a command line interface is obviously essential. Something that I didn't expect is actually having hardware integration, and I'm gonna mention that in a bit in another slide. But the idea that we can have a hardware device which is also able to automatically push things up into the platform. This is all built on AWS Batch and AWS S3, so object storage. The next, so getting data in, this is sort of something you can imagine is very simple. Actually, one sort of nuance here, because I don't think I'm going to run out of time. One of the design decisions we made really early on that I thought that maybe would be appreciated by this group a little bit more than other people would be the notion of how we organize data. And we decided to say we're going to think of data as being organized into data sets. Okay, sure. A data set is a collection of files. That's it. A data set is a collection of files. We're entirely file object oriented. Maybe one of those files can be a Parquet file and you can treat it like a database. That's fine. But then when we have a collection of files, we get to do very, very minimal typing on it. And it's entirely sort of like file name structure. So if I say I have a paired end FASTQ, if I have a paired DNA-seq data set, it's going to expect files that are in FASTQ format. That's the format. But also, that data set now is eligible to be analyzed by workflows which are expecting paired DNA-seq data. So it's, so we have, I don't remember exactly how many different data types we have here, but we have things like for images, I think up on the screen it says RNA-seq right there. So FASTQs could be DNA, could be RNA. Why would I call those something differently? Well, it's because I don't want to upload RNA-seq data and then ask, oh, am I going to run serif variant calling on it? It shouldn't be run on it, right? It's the wrong data type. And so we want to pair the workflows with the data type. Okay, that was a bit more of a digression than I anticipated. But getting the data in is actually a little bit more interesting than I thought it would be. Big part of this, scientific workflows. We're all here to talk about workflows. When you want to, I spent a long time trying to help other scientists analyze their data. When I got to the Hutch, I was a very early adopter of Nextflow. A lot of people call me, oh, that guy who does Nextflow. And a lot of times I was saying, hey, you want to do a thing? I'm not going to do it for you. I'm going to write some Nextflow. I'm going to give it to you. I'm going to point you to NF-core, and I'm going to train you so you can run it on the cluster. That worked sometimes. It worked much better than anything else I'd ever done before. The most success I had ever had with helping other people run workflows, I think by far and away NF-core has been the most successful thing I've ever had. And I think, honestly, the reason that I was given the opportunity to do more in my organization was because of how useful Nextflow has been for researchers. And I think that when you think about the collection of researchers who need their data analyzed, you'll understand that there is a segment of people that will run things from the command line, and there is another segment of people who haven't learned the command line, and asking them to log onto the cluster is asking them to learn something new. And so when I say that's worked for some people, I'm not being trying to be facetious. What I'm really saying is there is a broad collection of people who want to analyze data but don't know the command line. And I think that there might be some debate as to whether or not you put analysis tools in their hands or you ask them to collaborate with a bioinformatician. I'm agnostic on that. But we did want to make a point-and-click interface for being able to launch workflows. So a lot of this is, obviously, a lot of the foundation of this has already been pioneered in NF-core. You look at the schema for parameters, and you say this is actually very, very close in format, unfortunately not identical, but close in format to the React JSON schema that you would use if you want to generate a web form, right? And the NF-core schemas are used to generate web forms, which is great. So we use that as a starting place. We had to add a number of different sort of like platform-specific things. We want to say, let's make a place where people can click on a data set, click on a workflow, select all the parameters, click run, and have that just launch inside their account. That's very important. Another big part about running workflows has been letting people add their own workflows. So giving them the tool to make their own form, specify their own workflow, click add. And this is, I think, the tool for people like us, for bioinformaticians. I want to make a new tool, and I want to give it to my collaborator and say, you run it. I'm not running it for you. You run it on your data. I turned it into a button in the data platform for you. And that's something that I find really satisfying when I see bioinformaticians at my organization who have started doing that. That's very early days. Okay, so that was the workflow digression for this particular conference. Big part of the platform has been connecting directly to instruments. So we have a hardware device on premise. It's a storage gateway from AWS. You drop files on it. It just looks like a shared folder. Those get streamed up into AWS. You can set up a we have set up a Lambda trigger in there, which puts them into the right account. What this means is data comes off the instrument. So I think that flow cytometers were the first ones we did. There's a number of other ones that are going through, like proteomics data. They drag and drop onto a folder. It goes into the customer's account, the lab's account, and then they get an automatic email saying, hey, your data is available. Click on this link to go find it. That's really huge for automating and streamlining processes from the core resources, which I think are a huge asset at Fred Hutch. Being able to say workflows are great, but there might be other types of compute you want to run. So you might want to launch an interactive notebook. You can do that in Xero itself. We have a SageMaker interface, which is nice. Being able to pick what kind of compute instance. I want to do something big. I'm going to rent a ½ terabyte of RAM, but I'm only going to do it for a couple hours. That's wonderful. Also, being able to pull the data down directly in Python or R and saying, I want to run my custom stats. The data table I'm loading is actually a file in my account in Zero. I can access that in an authenticated way and just load it directly into my live Python session. I think is a really nice way of making sure that like the canonical copy of the raw data always is in this one place. You can control access to it. And then I know, hey, I ran this analysis. If I give this notebook to my buddy who has the same access, they can run it. And I know that the input data is coming from the same place without copying files around, which is nice. Getting to the larger organization. So that's something that this is much more intended for sort of the bioinformatics people that want to get into in an interactive session. Account management turns out to be huge. So this is really, how do you give people access to the data that you're delivering to them from the point of view of the bioinformatician? And how do you, as a PI, make sure that your lab members have access to the right data? How do the IT professionals ensure that each lab is only seeing their data with proper security? And also, how does IT get out of the business of answering tickets to add and remove people? A PI says, I want to add person X. IT doesn't have to go on the back end and say, click, 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 add person X. That's just time that they don't have to spend. So turning that into a menu interface directly in the website has been actually amazingly popular. Very simple, based on AWS Cognito, not terribly complex. This also includes one of the big issues with cloud computing, which is cost anxiety. I want to make sure I don't get a $10,000 weekend. Allowing the PI to go in and set, this is how much money I'm willing to spend in a month, in a quarter, in a year. When I get to 50%, send me an email. When I get to 75%, send me an email. When I hit 100%, just turn off all the compute and make sure I don't spend way too much money. All the data stays there. We just turn off the compute. This actually happened earlier today on an account, which is good. And this is something that means you don't get surprised, and I think this also really helps with the communication. What am I getting? What resources do I have access to? Can I make sure that I'm not spending my own budget in a way that I'm not expecting to? So that's really important from the larger organizational sense. This, I think, is also a reflection of the way that our group is set up. So this is something that really makes the most sense when you think about a number of relatively autonomous groups operating with a fair degree of budgetary independence. We have over 200 labs. They each manage their own grants. They're each in charge of their own budgets. And so we really had to put the control in their hand, whereas if we were in a top-down organization, it might be, sort of insane to say, oh, the person at this level is able to say, I want to spend $10,000, whereas the approval might need to go up the chain. So this is also a reflection of what it's like to work at a biomedical research institution, which is essentially a collection of autonomous labs, which I think is sort of like a sociological reflection. The bit that I'm actually going to spend a minute on, because I have time. I have no idea what time it is. I think I have time. OK, great. So I want to talk a little bit about interactive visualizations, and this is the last bit. So obviously, multi-QSU is amazing. You run a workflow, you open up, you double-click, and you can immediately get an idea of what happened. I think this is a great example of the type of visualization that makes the results more accessible, and they also it streamlines the process of doing science. Obviously, all the data is there, but when you have it formatted in a nice display, you can have someone say, I'm going to click run, or I'm going to just go log in to see the results that came off the sequencer. And instead of having to load something into Python or R, which maybe they can do, maybe they can't, instead of having to load something in and generate their own visualizations, instead of having to download data locally, the more that we can display directly in the web portal, the more value there is for the data that's being hosted there. And this is something that was, in a large way, one of the big carrots that we had for ourselves when we started building. This was actually one of the driving factors in the way that the entire system is built, is that we want to make sure that we can deliver data visualizations privately or publicly if you decide to publish the results, but within the context of collaborative research, that a defined group of people can access and view the data that they're generating. So I have some examples up here of different types of visualization. So, multi-QC, so any sort of HTML, obviously. We put IGV into the browser, or we added IGV, so you can look at genome tracks, which is really nice. A molecular image viewer. At the bottom, I have, bottom's IGV. Oh, right, in the middle, we have a really nice charting interface. So taking tabular data, pulling it in, actually using DuckDB. So I really enjoyed that DuckDB talk. But being able to merge data and then put it into eCharts. So you can just go through a menu and say, I want a scatter plot. I want the X to be this. I want the Y to be this, and sort of set it up all yourself. I really like that sort of like flexible interface, and there's a lot more to do on that side of things. However, there is another part of it, which I'll show you right before I have my credits here. And this is an example of spatial transcriptomics. So, okay, this is something I'm really excited about. Spatial transcriptomics, you got a piece of tissue, put it in a microscope, take a picture, then you use a machine that measures gene expression across a bunch of different dots, so you can see what genes are being expressed in all these different spots. You do it with Space Ranger does the analysis, gives you a nice HTML summary, which is pretty good. You can actually download the data, a couple gigabytes, and load it up in the Loop browser, which is nice. So if you are, if you're comfortable moving that much data around, a lot of people use something called the Loop browser, which is cool. There's also this amazing library out there which lets you visualize that data directly in the browser. So this is an example of a public data set from the Cell Ranger website from 10x. But the idea is that you have all of this gene expression across lots of different spots. You also have microscopy data, and you can actually just zoom into it and explore it directly in the browser. One of the things that's really amazing here is that you can explore all the different genes that differentiate clusters of cells, like cell types. And you can mouse over them, and you can click on each one and say, I want to see where each gene is being expressed. And so you can imagine someone saying, hey, I did spatial transcriptomics. I'm really interested in this bit of tissue and this bit of tissue. So I'm going to go see what genes are expressed differently. I'm going to sort of I'm going to like leaf through them. I can color everything, make figures for your plot if you want to. And sort of like customize all this stuff. And maybe for some people, that's what they wanted to get out of this. Maybe that was the goal of doing spatial transcriptomics, was to really look at just identifying a couple of gene signatures and then moving on with your life. And if that were the goal, then they would be able to come here, look at this, explore their data set, and then move on with their life, having just done spatial transcriptomics done through our sequencing core without having to open the command line or download any files. So this is very early days. This is something that honestly is not actually in production yet. This is from our development side, so I'm not gonna say that we've solved this problem. But being able to complete that process of the data comes in, it's managed, it's analyzed, and then it gets put in front of a scientist within a secure, cost-controlled environment in a way that they can get what they need out of it to move on and not think about data analysis anymore. That's really my dream as a bioinformatician. And so that's something that I'm really happy to be able to have shared with you. We have a couple of examples of sort of what it's been like as we've scaled up. We've learned a lot of lessons as we've gone from a couple of users to a lot of users, from a couple data sets to thousands of data sets. I think I've covered most of these through the talk in general. And so to leave a couple minutes for questions, I want to say there is this much larger group of people that have contributed to this. It has been a massive team effort. I'm really, really thankful for the environment at the Hutch that we have, as well as the support we've had from AWS, which includes the recent AWS Imagine grant, which we're really lucky to have been recipients of this year. And I'll leave my contact information, and thank you all very much for your attention.
Thank you, Sam. That was a very impressive presentation. Very cool functionality as well. I have a question for you. Does Zero implement any of the GA4GH standards for connecting to other repositories, data repositories, workflow repositories?
It's a very good question. So we have not yet. We are very interested in that. We've been looking at APIs to connect between different data sources. Actually, one of the first ones that we've been looking at has actually not been the GA4GH, but instead the FHIR API. So for connecting to clinical databases, which is something that's very interesting. But I'd say that something like GA4GH, and also in a larger sense, making this a data repository that is very easily accessible from the outside is very much in our plans for the larger architecture. So that's somewhere we definitely want to go.
That's wonderful to hear.
Yeah.
Very cool. Thank you so much. If there are any follow-up questions, well, we're going to have the coffee break now, so please give another hand of applause for Sam and the rest of our speakers this morning. We're going to break for coffee for half an hour. I'd like you to make sure to pay attention attention to our sponsor tables over there on that side of the table. They have swag. They don't want to fly home with it, so make sure to go. ZX Discovery has these very cool plug adapter thingies. Super cool. Enjoy the break, and we'll see you again here in half an hour. Thank you.
Oh baby, I wanted you to be here inside my arms where the night goes down. Oh baby, I wanted you to be here when the sun comes up and the day goes by.
All right, everyone, we're going to start again in a couple of minutes. So please wrap up your conversations and we'll get started on time at 11:30 in 3 minutes. Thank you. All right, everyone, we are going to start up again now. Please return to your seats so we can start the second session. All right, thank you, everyone. Okay, welcome back to our second session of this morning, of the second day of the Nextflow Summit. We have another great lineup of speakers for you now, running until lunch. And we are going to start specifically with Stephen Rudd, who is going to talk to us about Nextflow and nanopores. Thank you.
So I'm a bioinformatician, and I'm also a product manager. This gives me the opportunity to talk big, not to focus on any of the specifics. We're going to go fast. I've got 15 minutes. I've got my colleagues Chris and Rachel, and they're going to be delighted to jump in and answer any of the questions. So I'm coming from Oxford Nanopore Technologies. At Oxford Nanopore, we perform DNA sequencing. The way we do DNA sequencing, as Adam Philippi introduced yesterday, is we've got a fist. This is your nanopore. We've got a 2-kilometer cable of DNA sequence, and we run it through at hundreds of feet a second. Technology is really cool. It's miniaturized. And, hey, we've got a beautiful marketing slide that's trying to give us the essence of what is the technology and how does it actually work. Okay, technology, marketing, base calling, it just gets, to a point. Let's actually have a look at the individual DNA sequencing device. This is the flow cell. The flow cell is what we generate data on. It's small, it's inexpensive, and it allows us to produce data that comes in a wide variety of different sizes, different shapes. But essentially, what we're imagining is they could be anywhere between sort of perhaps 1 and 50 million sequence reads. There can be a massive diversity in the actual lengths of the sequences. And we need to begin to imagine how can we, as a technology, help our users move in interesting sorts of directions. So one of the first things we had to have a think about is what are the user personas that we need to really address? At the top of the screen here, you can see that our corporate goal is to enable the analysis of anything by anyone, anywhere. We have DNA sequencing devices that we can take out into the field. We've got DNA sequencing devices that have been to the International Space Station. We have people DNA sequencing in hostile environments, being both the Antarctic, the Arctic, being in all sorts of hostile marine and desert environments. This means that if we're truly going to democratize the sequencing, should we also not be bringing bioinformatics to these same users? This means that the users, shown in the first panel, could range from molecular biologists who are doing field research, through to astronauts who are sort of floating around in the space station and need to understand, is that biofilm that is rapidly proliferating on their spacecraft going to generate a big problem, and should they stay in space forever? Well, okay, that's perhaps a bit far-fetched, but we have got a number of personas. We've got a number of users that include both the bioinformatics professionals and people who aspire to at least getting some results out of their bioinformatics process. So, okay, perhaps we can address anyone. The next thing is how we're actually going to facilitate this bioinformatics. We've heard a lot about cloud. Yes, send everything into the cloud. Well, actually, if you're in the desert and your nearest cell phone tower is a long, long way away, then probably cloud isn't the right sort of solution. So this is where we've been trying to challenge some of the dogma and say, okay, bioinformatics, should we not actually do this on the sequencing device? Should we not do this on the computer that is attached to the sequencing device? Yes, majority of our users are Windows users. Should we be supporting or facilitating bioinformatics on Windows? Heresy, horrible thought. Why would you possibly do that? But hey, 80% of our users are using Windows, and if we're trying to exclude them from the ecosystem, then there's a little bit of a challenge. So we need to support different platforms, we need to support cloud, and then we need to look at the magnificent diversity of what are the sort of science and workflow that we should be supporting, tolerating, or encouraging. So what is our solution to this? Our solution to this is something called Epitome. See Chris, in the next break, you can see it's shiny, it's beautiful, it's on the desktop. But this is our platform that we use to help all of those user personas get towards a tractable bioinformatics analysis. It is a standalone desktop application. We should have several asterisks here because it's not truly standalone. If you're on Windows, you need WSL. WSL comes crammed full of interesting things like, we've got Docker stuff, and we've got Java, and we've got Nextflow, we've got all these complicated things, but essentially it's a standalone application with a terrific amount of engineering behind it to hopefully provide our users with a one-click experience towards bioinformatics. So, okay, it's a dull slide. Let's move on to things which are a little bit more interesting. So last year, I had the great pleasure of joining some of you folks in Barcelona. And at Barcelona, we outed Oxford Nanopore as a company that was using Nextflow, and we talked about some of the warts in the Nextflow ecosystem and some of the warts in our implementation. But essentially, we had a really ugly solution to helping users move forwards. We had engineered into a Jupyter environment an ability to run Nextflow workflows to produce these reports, and we had this kind of wonky sort of ecosystem that was sort of working. It wasn't too bad. Everything was Docker and Conda, and we've been pulling our hair out. You can see, not much hair left. How do we actually support users in Conda? Conda, it's great, but it's also rubbish at exactly the same time. So, okay, yep. We had, things sort of working out, and we said the horizon is going to be an integrated application. We're going to move everything over towards Electron. It's going to be beautiful. We're not going to have any of the horrors of Jupyter. Yes. We had kind of a lot of fun last time. So this time, I'm just going to give us a little bit of an update as to where we are at the moment. And, are we still happy with Nextflow, or are we going to have to implement our own solution? Well, I'm talking here, so we probably know the answer. Anyhow, Electron app, Epitome desktop, open source. It's friendly, accessible. We launched it at our London Calling event in June this year. It's colorful, it's beautiful. It's designed for non-bioinformaticians. It's designed for people who don't have the sort of resources of the Broad or the Fred Hutch. It's designed for people who, we want to get started with bioinformatics. We want a button to push, but we don't have administrators, we don't have helpers who can help us through the problems. We want to make it easy to get started. And really here, getting started with bioinformatics is trying to help users generate a colorful figure with as few clicks as possible to give them this sense of control. Beautiful figure, I'm in control of my data. I understand that the sequence quality was adequate, I understand the results are fine. We're in a position that we can move forwards and proceed through the ecosystem. Anyhow, majority of folks in this room here are bioinformaticians. You don't want a single button to click. You want to hear a little bit about, actually, how can you use some of this Nanopore goodness from the command line, from your own data centers. So we have what we call Epitome workflows. The Epitome workflows are just normal Nextflow workflows. We are somewhat adherent to some of the NF core standards. We do very much like the NF core schema. This provides us with a framework that is somewhat interoperable, but somewhat not. It's designed to be something that makes a lot of sense for our users, and it's really working towards what are the best practices. We want the code to be literate. We want to help you, the professional bioinformaticians, see how we, the Nanopore experts, would recommend that you solve particular problems with the particular software environments that have been tested and validated by our own teams. We appreciate that command line is probably the cleanest way to go. With the command line, you can do the orchestration. You can go and integrate with the various systems that you have in-house. So really, Chris and his team are very much thinking about how can we actually run things in our own environment. We have our own HPC. We have an ability to use CPU, GPU nodes. We've got all sorts of different flavors of goodness in-house. And we find that having Nextflow, our sort of epitome flow, workflows, that's the cleanest way to get started. It all makes sense, and it appears to be helping us towards the democratization of bioinformatics. The key point here is that we are not producing a black box, we are not supporting a black box, and everything is going straight through to GitHub. GitHub is where all the goodness lives. 18 workflows, they are supported, and we encourage you to have a play. We want to have merge requests. We want to have pointers as to things that are broken. We really want to sort of understand what we can do to make our products a little bit more appropriate to your own needs. On the left-hand side, we've also got our own web page. The web pages are trying to describe the product. And again, here, we're trying to create a little bit of community amongst these neo-informaticians. These are the biologists who want to do a little bit of bioinformatics, don't really know what anything really means. So we're trying to create blog posts. We're trying to draw the users into the story. We're trying to educate, and we're trying to demystify some of what is going on in the ecosystem. So anyhow, labs.epitome.io, a great place to go. It's going to point you onto the GitHub, and there is all of the goodness. So let's have a look at what are the sort of workflows that we're trying to support. We've got 18 different workflows. I don't have 18 slides because that would get a little bit tedious after about number 2. I just wanted to give a little bit of a sort of insight as to the diversity that we're trying to support. So this slide that looks very different on my desktop to the way it looks here, go figure, it's talking about amplicon sequencing. So amplicon sequencing is just you do a PCR and you want to sequence your PCR product. Really simple, really trivial. The amount of money that people are spending on doing this with other technologies, such as Sanger sequencing, you could actually do this with our technology, a little bit cheaper. We're trying to release a workflow here that takes the canon of an old, tried, tested technology, and we're trying to reinvigorate it for today. So, simple workflow. We've got an integrated protocol that works on the molecular biology side, through to the informatics that you can run on the same sequencing device or the sequencing machine that you have. We're aiming to go and consume the data, to report it, to make it visible, functional, and literate, so that a user can go, yep, this amplicon is exactly what I thought it was. I see no evidence for an inversion. I see no evidence for any nucleotides being lost. I'm happy. Let's proceed with the molecular biology or the rest of my study. So amplicon sequencing, great example of simple science that we're trying to open up to our users who are not experienced in sequence alignment or in de novo assembly of short fragments. At the other end of the spectrum, we have whole human genome sequencing. So whole human genome sequencing has been mentioned a number of times in this forum. The concept is you start off with a blood draw, you start off with a piece of tissue, you want to get towards the genome, and you want to call different genetic variants. We've got a sort of a Nanopore marketing campaign at the moment, and it's called, what you're missing matters. Nanopore sequencing gives you ability to look natively at the methylation. You can get SNPs, you can get structural variants, you can get copy number variants. With all of these different sorts of variation, not to forget, of course, variable number tandem repeats or the VNTRs or we've got loads and loads of different genetic variation. So we want to have an integrated workflow where, of course, you start off with your sample, you sequence, the machine goes ping, click on the button, you process the data, and then you have the collection of variant files. You've got the methylation data. You can come up with all sorts of magical, colorful plots. You have the ability to understand what is the etiology of this rare disease, what are the particular functional variants that we should be characterizing or segmenting. So, hey, beautiful piece of work, and it's really making the analysis of whole human genomes a single click for the people who are beginning to get started with their genome analyses. So we've been talking about bioinformatics on the box. We've been talking about bioinformatics, on your sort of laptop. You can do it anywhere. But one of the things that we've been working towards recently is the concept that we need to run all of our workflows in the cloud. So cloud is both great and it's terrible, depending upon where you are and the regulatory environment that you're operating in. I'm often dealing with Windows users. A Windows laptop, when you're trying to process single-cell type data, does not for happy users make. We need to give them the ability to have a seamless story where they can go from problem data through to colorful report and the ability to go and open up the Loop browser. How do we do this? Well, we're offering our own cloud sort of plugin. What you do, you're presented with a button. You log in. Would you like to run this analysis on your device, or would you like to run it in the cloud? Hey, I want to run this in the cloud. Machine does a little bit of chewing, and it gives you a complicated number that is an instance or something, or something technical in the cloud. You have to ask Chris exactly what's going on. But from this colorful picture, you then have your workflow running. You get the green bars that individual processes have run to completion. We are in control. Everything is looking great. And the only difference is when we look through some of the log files, we can see that we actually have particular Amazon endpoints where all of the data has been orchestrated and fed forward. This is designed to be a product that is accessible to all of our users, and we have this as an integral part of our Epitome product, and this will be going live in the next few weeks. So what else is coming? Well, hey, we've been talking about Nextflow. We've been talking about how we can begin to sort of integrate Nextflow workflows to make life easier for our users. We're now at the stage where we're beginning to integrate our platform with all sorts of third parties. This brings additional interpretative context to the analysis. Of course, we're upskilling all of these third parties in how to use our Nextflow products, but this is beginning to open up all sorts of new opportunities, challenges and ways that we can collectively move forwards. So super exciting stuff. I mentioned last time that yes, it would be great. We want to help you get your workflows into the Epitome environment. Is this not a way that we can all share our favorite workflows with users who are not quite ready to get started in true bioinformatics? We have a couple of contributions to our Epitome environment. The first one is a piece of software called EMU. EMU performs 16S ribosomal RNA classification. Really simple sort of science, but it's a really nice plugin, and it is an alternative to the more traditional Kraken sort of K-type classifications that have been used. So hey, everything's going in the right direction. I'm 20 seconds already over. Yeah, we've got a load of summary points. Everything is in control. Everything is wonderful. The final ticket here for sort of Paolo was the fact that, yes, we are still meant to be implementing a perfect workflow management software. We're not quite there yet. Chris didn't give me anything mean to say this time. We'll save that for next time. Thank you very much.
Thank you for the very energetic talk and very informative. One quick question, because I'm sure a lot of people are wondering, the epitome functionality that sends the analysis to the cloud, do you pay for it? Do we pay for it? Like, how does the billing work on that?
Yeah, there are certain questions that you really shouldn't ask. The answer at the moment is this is a service to run our workflows at our cost for our customers. This could change at some point in the future. It depends how many people run our workflows.
Yeah, I can imagine that. Thank you so much. If there are any more questions, please ask in Slack. Thank you. And next up, whoops, I gotta pull up my, yes, next up we have Eleanor Karptatham, who is going to talk to us about using NF Core pipelines to analyze data from large files.
Hello, welcome, and thank you for having us here. We're here from the University of Oxford to discuss how we're using Nextflow pipelines in our lab. And I'm here today with my colleague Patrick.
Good morning, everyone. So my name is Patrick. I have a medical background. I've come to do a PhD and acquiring a lot of skills in immunology and increasingly bioinformatics.
I'm Eleanor. I'm a postdoc within the Knight Group, and currently I work on COVID. Mostly to do with vaccine immune genetics, but I have a background mostly in veterinary-based research, and I have to admit I am probably one of those scared of the black box scientists that we've all been discussing recently. So today we're just going to give you a brief talk. We're going to focus on the kind of interests that we have within the Knight Group, why we moved to Nextflow and how we're trying to implement those pipelines into our lab, and then a little bit about how we're using germline somatic variant discovery and vaccination data sets, a little bit how we're understanding epigenetic features in a sepsis data set, and then we're going to summarize this all up together. So the Centre for Human Genetics is where we're based, linked with the University of Oxford, and we belong to the Knight Lab. We're a relatively small lab as teams go. Anytime we have between 20 and 30 members. This ranges from professors to postdocs to undergrad and PhD students, all with a background that's quite mixed. We have some clinicians, some non-clinicians, and predominantly we're all wet lab-based scientists. Our main interests really are looking to understand how genetic variation impacts appropriate immune responses to a whole range of diseases. These include COVID, sepsis, ankylosing spondylitis, among many others. And predominantly we're using large next-generation data sets to do this, and these range from anywhere from 10 participants to about 5,000. And at the moment we're using a high-performance computer cluster with a Slurm scheduler, and historically we've had a lot of bash scripts that haven't been necessarily well maintained. They have a limited version control, and they don't have much dependency management.
So I've been very interested in bringing Nextflow into the lab as part of my PhD. I think really for the reasons that Ellie mentioned. So we have had, at times, excellent bioinformaticians, but then gaps as well. And we inherited a lot of scripts without much in the way of modern software engineering practices, and we don't really have the resources to implement them ourselves. So Nextflow, and in particular the NF Core community pipelines, are very attractive to us. They really offer the opportunity to standardize the pipelines across different projects within the lab, often where we're doing the same relatively kind of straightforward things on large cohorts, and it's very important to maximize reproducibility as much as possible. We've also found, with many students in particular coming into the lab from wet lab and clinical backgrounds, it often can be a pretty steep learning curve, as everyone else has mentioned, getting to grips with the command line. And using Nextflow, and particularly the NF Core pipelines, is really right in the sweet spot where we can bring someone in, and within days or weeks, they can be seeing great results from their data sets.
Okay, so briefly a little bit of background about what we work on. I'm not going to spend much time talking about COVID-19. I'm sure we all know it. I'm sure we all felt the impacts. But it is important to consider that vaccination was a huge effort to control the pandemic. And as of like mid-November, about 13.5 billion vaccine doses were given across the globe. A massive effort by research scientists across the world in order to work out how we make these vaccines, how we give them, what they work for, and who is protected. But actually, when we consider this, there's still a huge number of people across the world who don't mount a good immune response to COVID vaccine. You either have underlying health conditions, age is an impact, and most importantly, human genetics underlie reasons why people have a low immune response. So one of the main questions that I'm working on in the night group is like, is there a genetic association to lower response to vaccination? And in this instance, it's related to the COVID vaccine, but really more broadly, do we see any reasons in multiple modalities why that might be the case? So we formed the COVID-19 Vaccine Immune Genetics Project we call COVID, in collaboration with the ONS, which is the Office for National Statistics in the UK. We invited 5,000 participants who either had a low or high antibody response. So when the pandemic kicked off in the UK, the ONS made a long-term study where they enrolled participants from about 500,000 households, and every month you had an antibody test. So we're using data from that to try and split our cohort into really low or non-responder and really high max responder. And we've collected quite a lot of data. So we have genotyping data, HLA typing, whole exome, and DNA methylation. And for this project, I'm hoping to use these Nextflow pipelines to really understand this whole exome and this DNA methylation. So quickly, we're just using the SAREC pipeline here to answer questions like, are there rare and limited variants found that cause functional changes in proteins relating to antibody binding that could impact vaccine response? Do we see these variants in just the low responders? And if so, could we classify these? Could we understand that a bit better? And also, are these low response phenotypes driven by really rare penetrant genetic variants? And do these contribute to this increase or decrease in antibody response either way? So at the moment, I've been running the NF core SAREC germline pipeline to analyze these whole exomes. I have about 750 whole exomes, and I found that SAREC and Nextflow is great. You can put them all in, it puts it all together, it has all these nice modules. I've personally been using multiple haplotype callers, so I'm using the deep variant, the freebase, and the haplotype, and I'm concatenating these together. And then it's great that you can have that with VAP already plugged in, as well as the associated plugins that I can then add on to VEP. And at the moment, I'm looking into whether I could also use the NF Cause Rare Disease pipeline. I found this is a really great way for someone who's predominantly wet lab like me to sort of get into this field, to understand better, and with such a great community to learn from.
Thank you, Ellie. So a little bit of background on my project as well. So I'm interested more on the epigenetic side, looking at the causes of immune dysfunction in the period after critical infection. So this comes out of really the clinical and epidemiological observation that people who survive critical infections show changes in their immune function which can persist for several months after they leave the ICU. And these are measurable, but the next step is really understanding the mechanism behind them. And we aim to link these phenotypes to measurable epigenetic features, so particularly DNA methylation, histone modifications in different immune cell types, which culminates on the question of what are the epigenetic consequences of sepsis. And the resource for this is our Sepsis Immunomics project. So we're getting to around 400 participants, and we have then performed a number of multi-omic assays, so particularly DNA methylation, transcriptomics, and somatic variant-oriented target capture sequencing. And really for each of those blocks, I've found that the NF core pipelines have just been fantastic for accelerating the analysis that I need to do. To give a quick sense of what this looks like, so this boils down to the question of which DNA methylation sites vary between our post-sepsis patients and then age and sex-matched controls who we've also recruited and sampled from. I found that at every step of the way, the methyl-seq pipeline has supported what I need to do. So we're using an assay which is relatively new, so a targeted enzymatic methylation conversion assay, and all of the features for a target assay are really there, and I've been quite surprised by sort of how little I've had to add on so far. We've also found that it works just perfectly with our existing cluster. So we've scaled up from dozens to now hundreds of samples without any drop-off in performance. And we see that the data that comes out of the pipeline is of excellent quality, so very nice methylation QC, and we're starting to see some very interesting epigenetic findings which we'll follow up with further functional wet lab experiments. So in conclusion, we think this has probably been a fairly light talk, but just to give a sense of what Nextflow and in particular the NF core pipelines look like when they're deployed in a kind of medium scale, mostly clinical, partly wet lab group like ours. It's been a fantastic tool for improving reproducibility and scalability across our analyses, and has really allowed us as predominantly wet lab biologists and clinicians to go a lot further with our analyses. And it's been great to be at the conference learning a bit more from the software engineering side about future directions.
We have a lot of people to thank contributing to all our work here, but I would also like to thank Pat. Pat brought Nextflow into the lab. He's helped me train on Nextflow. I think it's been a really great addition to our team, and it's been really nice to be here and listen to all the talks.
Thank you so much, both of you. Very interesting talk. Do you see any, I may have missed this, but do you see any opportunity to contribute back some of the pipelines to NF Core or something like that? Would you be interested?
Yeah, certainly. I think that's something we're looking to do more of as we gain experience and then can start to suggest extra things. But to be honest, we found that almost everything we need to do is implemented really well already. So
that's wonderful.
Yeah.
Thank you so much, both of you.
Thanks.
All right. All right. So next up, we have Mayur Khanna is going to talk to us about leveraging Nextflow in a distributed cloud infrastructure to analyze genetic data at scale.
Hi everyone, my name is Mayur. I am a data engineer at Pfizer, and I understand that given my employer I might have a unique perspective compared to some of the other speakers here, but I'd like to peel back that curtain and give you all an insight onto how we are leveraging Nextflow in a distributed cloud infrastructure to analyze genetic data at scale. So quick summary of the presentation. I'll begin by discussing some of the modern challenges we face with genetics research, and then dive into an overview of our platform, and then discuss some of the challenges and opportunities that we encountered with cloud computing and using our ingestion pipeline as an example for those use cases. So our team is situated in early stage drug discovery. So believe it or not, discovering drugs is a very long and expensive process. And the golden question, number one question on everyone's mind is targets that can be exploited to generate these therapeutics. And so a source of inspiration for these targets, we could look back to Bio 101 and look at some of the underlying biological principles to identify some of these targets. And so our research focuses on DNA variations that are derived from genome-wide association studies. So I'd like to point out the two main challenges with modern genetics research. One is just the massive scale of data available, and also the reason why we're all here, the challenge of reproducible research as well. So this graphic is taken from the GWAS catalog, which is the largest source of publicly available data of GWAS data. Currently, there's around 40,000 or so studies. As we can see, in recent times, there's just a sharp increase in the number of studies that have been made publicly available, which introduces, a very big data problem. And additionally, I don't need to belabor this point too much to this audience. Reproducible research is very challenging, and within a pharmaceutical organization, you have varying different skill levels, technical expertise, and also just preferences for languages and pipelines. And as was shown in the seminal Nextflow paper, there can even be inconsistencies in algorithms across multiple platforms. So this really provides a need for a standardized set of pipeline definitions in order to run these workflows. So from here, I'd like to introduce the Genetic Informatics Platform. So this is a resource we've developed that really enables reproducible workflows through a distributed cloud infrastructure and provides an internalized genetics data repository. So to give an overview of the GIP, I would say there's 4 main components. One is a set of visualization tools to aid in hypothesis generalization and target identification. We also have a service that serves individual linkage disequilibrium data, so essentially to see the uneven inheritance patterns between alleles. And then additionally, we have that centralized data repository in addition to individual pipeline outputs from user-defined workflows. And then finally, we leverage Nextflow in a AWS batch system to run these processes on the cloud. So just to give an overview of how we're specifically using Nextflow in our setup, so there's 2 main implementations. One, we have a set of standardized pipelines that we have developed internally and made available to our users. And so we have multiple modalities in which these pipelines can be accessed. So we have a user interface for those folks who are just want a point-and-click solution and can access those resources through there. And additionally, we have a command line interface to provide a wrapper for all these functionalities, and then also an API to do more programmatic access for these workflows. And so additionally, we also enable users to implement their own workflows. So the 2 main components for that is as long as they have a Docker container and their Nextflow definition along with a configuration file, you're able to then leverage our cloud infrastructure. And as discussed earlier today, we use AWS Batch as our executor of choice, and that allows us to get the nice reproducibility features that Nextflow provides. And from here, I think this really presents one of the biggest, in my opinion, opportunities of cloud computing, is that it enables dynamic vertical and horizontal scaling. So I know we've all been in that situation on the HPC where you go to submit your job and you see that there's 10,000 jobs ahead of you in the queue, and you're left waiting hours, if not days, to run your analysis. So with the cloud, I like to think that we have access to an unlimited amount of resources, and so this allows you to tailor your workflow and get those resources on demand while also being efficient because cost is important for this type of cloud infrastructure where you can scale it down to as little resources as you need. And additionally, sometimes the workflows that you're running just exceed the hardware limitations within your HPC, and so having this resource really now allows you to expand beyond what you might be limited to with an on-prem resource. And so for the next part of the presentation, I'll dive into our internalized genetics data repository. So we're calling it the GWAS-DB. So this really is a process that is driven by Nextflow to ingest this large amount of data into our columnar database, which is run on the AWS Redshift platform. So what are the data sources for this resource? So we have internalized the GWAS catalog. So we have almost all of the 40,000 studies internalized into a standardized database, which can be queried by our users through a variety of different modalities. And then also any internal studies that are available to us are integrated into the system as well. So one of the limitations mentioned from the GWAS catalog themselves is that they're unable to perform this cross-study analysis, right? So what we've been able to achieve is cross-study analysis, and one of the ways that we're able to do this is through the standardized database, and these are 2 screenshots from the user interface. So the graphic on the left is a locus zoom plot. So essentially what this does is you take a phenotype of interest, and it returns all of the variants that are associated with a specific gene or locus of interest, and it's fairly performant. So you can query hundreds or thousands of studies in a matter of seconds. So you can mouse over individual variants and see the associations across different studies that map to that phenotype. And from there, you can select one variant and generate additional visualizations such as PheWAS. And in this instance, I've shown a PheWAS forest plot where it shows associations of that variant with other phenotypes. So within the drug discovery context, this is really important because let's say you're targeting a variant that affects kidney function. You don't also want it to increase blood pressure or be associated with an adverse phenotype, which could lead to unintended side effects. So I've shown you what the GeoSDB is, and now the question is, how did we internalize this data? And this really is a process that's Nextflow pipeline that's really leveraging the cloud infrastructure that we've built. So the first step is a harmonization step. So essentially, this is the process where we take those GWAS inputs and standardize it to a set of common column types. So this is one challenge not specific to the cloud, but one that does require a manual mapping of these column names to those common types. And then additionally, in this process, we also flip alleles in the instance where reference and alternate alleles are not matching, and then update RSID values based on the RSDB SNP. And then also, if there are any missing neglog p-values, we calculate them in this step. From this, we output a VCF file, which is then fed into the next step. If necessary, is then to lift over the files. So we're utilizing the Picard software from the Broad Institute. And so essentially what this does is it lifts coordinates from one human reference build to another. So in this instance, we are targeting HG38 to ensure that all the studies in our database are mapped to a common set of human coordinates. And one of the challenges with this process is that it requires large reference input files. And so, the naive approach would be to stage those files every single time, but that's a very redundant process and can also rack up costs with unnecessary I/O operations. So one of the solutions we found for this, and also an opportunity of cloud computing, is the utilization of FSX network drives. So this is a Lustre drive that essentially allows you to perform those same I/O operations over a network connection, thus eliminating the need to stage these large reference files. And the really nice thing about the FSX implementation is that you're able to simply map it to an S3 bucket location, and then it automatically is available in that shared drive. And this really alleviates the need to manage duplicate copies of data and really allows for one source of that information. And then some final quality control steps that we've implemented. So one step is to calculate an estimation of p-values derived from the effect size. And essentially, then we compare this with the p-values provided by the source. And so if there are any deviations beyond a set threshold, that study would be flagged for manual review. And then also any errors that may arise from underflow of neglog p-values are also fixed in this step. And then from here, we are then ready to ingest it into the GWAS database. So we take these VCF files and convert it into a Parquet format, and then begin the process to integrate it into the Redshift database. So one of the challenges with columnar type databases is that these insert operations can be very expensive. So we employ the use of multiple staging tables, and this process still takes a very long time, so it could be on the range from hours to days, depending on how many studies you are ingesting. So usually this is a process that's run over the weekend, and still is one of our pain points, but that's the solution we have implemented so far. And just to give some high-level statistics of the database, so right now we have over 38,000 studies internalized, referencing 32,000 distinct traits across 15 different populations. And so I put an asterisk by the distinct traits because they're not really distinct. This is a big curation problem that we have in the sense that the phenotype information that we're taking is directly from the annotations provided to the GWAS catalog. So for example, one study could annotate the phenotype as LDL, the other could be like free cholesterol, parentheses LDL, cholesterol LDL, and those would all be mapped to different phenotypes. So this is one challenge that we're still working on, and we are exploring NLP methodologies in addition to manual curation efforts to create a set of standardized ontologies to really aid in finalizing this database. So to conclude, I've presented how workflow management is essential for reproducible research. I've introduced the genetics informatics platform as a framework for the storage and analysis of genetic data on the cloud, and presented and discussed how cloud infrastructure offers many opportunities, but also unique challenges that must be addressed. And then finally, I showed how Nextflow can really drive the ingestion of GWAS data into our distributed database. So just some acknowledgements. This was a collaborative effort between internal and external collaborators. And I'd like to give a special shout out to Ben Alexander, our project lead, and Simeon Karstens, who's been an instrumental developer throughout this project. Thank you.
Thank you so much for this this very great talk. What's kind of your sense of the next challenges, the next steps for this platform? What are you looking at for the future?
Yeah, I would say there's two main challenges. One is adoption. We've provided these resources for our internal researchers, but we still have challenges for them to actually know how to use the platform, know how to use the API, the command line, or the UI. And then additionally, as I mentioned in the last slide, just that data curation problem. Mapping those phenotypes to a common set of ontologies is definitely a challenge.
Yeah, that's I think a challenge for everybody in the field. In terms of the adoption challenge for your, and that's your internal researchers, right? Do you find that it's a question of documentation or like educational resources, things like that, or is there a gap there that needs to be filled?
Yeah, definitely all of the above. Documentation is something that I'm ashamed to admit. It's something that I definitely need to be better at. But also just education of the resources that are available, because as we mentioned, when we're developing this platform, we're very much tunnel vision. We think it's very straightforward and easy to use, but to others it's just an enigma, and it can be challenging to adopt it for the first time.
Yeah, and I think I would say that's a challenge that a lot of us face in this field, and many people in the room, I'm sure, have had the challenge of needing to educate people on various tools and so on. Is there anything from the Nextflow point of side that you think that would be helpful if some of the stumbling blocks that your people are facing are working with Nextflow and that sort of thing, educational resources that we could be providing, something like that, would that be helpful?
Yeah, so I would say, I was using Nextflow before I joined my current position, and I've always been a really big supporter of it, but when I came to our group, I found that not many folks were utilizing that tool to begin with. So I think just increasing engagement and awareness of Nextflow and how straightforward it is to use. I understand there is a little bit of a steep learning curve, I will say. So maybe alleviating that process could be helpful for widespread adoption.
Yeah, I think that's a fairly common theme that emerges, and that is something we'll be working on, kind of bridging those gaps. And we're always really welcome feedback, specific feedback about the kinds of challenges people are facing, especially end users are facing, and we'll try to work with you. We'd be happy to collaborate to generate some resources to help with that. And that applies to everyone here, by the way. So just feel free to reach out on Slack, and we're happy to help. Find solutions to these problems, because I'm sure that a lot of the same thing will apply in a lot of different places. So thank you very much for your talk. And next we are going to be welcoming, thank you. I'm very happy to welcome Evan Floden to give us an overview of what's happening in the Nextflow ecosystem and at Seqera. Thank you very much.
Check mic. Cool. Thanks a lot, folks, for tuning up for day two. Yesterday, I gave a little bit of an introduction on the new branding that we've been pulled out over Seqera over the last month or so. Today, I'm going to go more into that, but also just go a little bit deeper into some of the new product features that we've been adding into Seqera platform. But starting off, sort of thinking about that rebranding, we had to do a little bit of soul searching, as I mentioned. We wanted to think about what was really core to Nextflow, and what was the kind of those values, or like product values, which flow through the rest of the work that we do. For us, it was three key things which came top of mind. The first was just this idea of flexibility. This idea that scientists want to use the tools that they're already using. They don't necessarily want to have to learn another tool or go into a particular learning a ton of new ways just to do the same thing over and over again. So when we think about that, we think about the ability to connect in with your Git resources, or the ability to connect into the cloud that you're using, almost kind of bring your own cloud approach. And that applies obviously for Nextflow at the workflow level, but also more broadly into many of the things we do. So the integration there with different compute platforms that we have. So this is, we're thinking about batch compute, things like AWS Batch, Azure Batch, Google Batch, the kind of workflow manager tools that are using that. We also think about the storage. Nextflow itself has almost left the storage and the data layer very much for the user to figure out themselves in most of the approach. I'm going to show some stuff later on around Data Explorer where we try and do this. We're going to take that same approach. So we're going to link in with the existing cloud resources or file systems that folks use. Also on the container technologies, containers have been really key to be able to provide the portability. And that portability in itself is what gives the community the ability to collaborate, to work on that same code base. And Paolo's going to be talking after lunch about some technology we've been releasing called Wave, which really goes into this further and allows us to take that container technology and really apply it for more scientific applications that we have. And of course, source code management is kind of key to all of this, the idea that you can have a single Git repository. I remember that first experience that you get when you say Nextflow run and you just drop that repository in there and it just really kind of pulls everything automatically. It provides a kind of a standard upon which we can all build things. Okay, beyond that flexibility, there's also this challenge with scale. And we've seen it the last couple of talks actually, where we're talking about how can you process all of this data at scale. So solving that problem is something we've been very much focused on and something that I think Nextflow does very well, and then we want to apply that to the other areas that we're going to solve. And finally, around open science, and kind of open science is central to this. When we think about the success of things like NF Core, it really came about from people being able to come together, collaborate, and build that. And there's no single organization or single individual or single place who can come and build that domain expertise, that kind of content in some sense. But by being able to have the technology platforms and ways that tools that we can integrate with, we can bring people together and to kind of build those tools out, which just become a fantastic scientific resource for all of us to leverage there as well. Okay, so modern biotech stack, how does this come about? So when we're thinking about this, obviously the modern piece is really driven from software itself. We talk about things being at the kind of forefront of technology here. Biotech more broadly used than specific like the biotech industry, but really around anything related to life sciences. And finally on stack here, we thought about this in terms of the software stack, which is not just a black box solution here, it's really a collection of tools that integrate well with the existing software that folks are using there as well. When we think about the sort of collection of tools and products we've been building out, obviously Nextflow has been core to that in workflow management, but we also have multi-QC now, which has been brought in thanks to Phil's involvement, and this is obviously something we want to continue to build out when we think about reporting, analytics, and also the aggregation of that, not just on a single execution, but more broadly when you want kind of more database-like functionality. Wave, which Paolo is going to be speaking about later on, but this is really a container provisioning service, as well as Fusion, which is a way which we can really mount the object storage like it's a file system in there. And I'll show you a short demo of some applications of that coming up as well. So this is kind of one view to see all those different layers in this. And if we think about the Seqera platform itself, we've got those integrations there with cloud, with HPC, with containers, with that storage layer, and then integrating an existing identity and code aspects to that. We also have the individual core tools themselves. So this is where you're able to run Nextflow pipelines, connect in with your results with multi-QC. And that kind of really the problem that we're trying to solve here, what people are actually doing with these tools around explore and management data, be able to launch pipelines and analyze notebooks. And that's what I'm going to show in a moment. Finally, it's been really important for us when we think about the different interfaces and different ways that people want to interact. Some people do want point-and-click interfaces, and they want to be able to make their resources available to other folks. So you want to be developing a pipeline, but make it available to the wet lab scientists. Or maybe you want to be able to develop it and basically run it through once in the GUI, but then afterwards, once you want to set that up in an automated way, you want to be calling it from API or CLI. And that kind of range of interfaces is really key to being able to get that experience across that as well. Finally, the way that this can be deployed as well is we have a cloud setup, which is what I'm going to be demoing, but there's also the ability to deploy this whole stack in your own environment, which then connects into the different resources that you're already using there. We like to describe this as the data analysis lifecycle, whether this is in some situations you're maybe more on the research side, where you're doing a lot of iteration, developing pipelines, developing tools, etc., connecting that in with your data, being able to run those analysis, interact with results, and then kind of the cycle continues. And when we think about where folks sit on that spectrum, we want to try and build something which is applicable to everyone there. Okay, so first off, starting off with pipelines and what we've been doing here. So obviously everyone knows what pipelines are used for. There's been a lot of examples over the last couple of days and so on this. When we look at what pipelines is doing currently in Seqera, we're able to build those, manage them, connect them into your cloud and your HPC. So it runs in a very similar way, essentially launching Nextflow as a service, but where Nextflow runs is in the environment where you typically run this, as well as have a UI for this and be able to see that. When we think about what we've been building more recently, we wanted to link in much more information about those pipelines, so almost like treating the pipeline entity like an object which can be tracked, which can have version control, etc. The costs has been really key. We've seen a couple of talks on that, understanding the costs associated with a particular execution, with a computer environment, as well as being able to work on that kind of scale and optimization. We see significant costs that are associated with running these pipelines at scale, and anything you can really do to optimize that. The work we've done with Fusion has been very promising in this regard, being able to save 50% sort of off the bat, starting off with that. So we kind of continue to push the limits of what's possible there, as well as define all of this as sort of infrastructure as code. Okay, demo time. So just go quickly, hopefully you can see the screen here. So I was a little bit resized. So I'm going to get a quick overview and demo of what we can do in pipelines today. So when I first log in here, you can see I've got a collection of pipelines which are ready to launch. Is that kind of big enough? Hopefully you can see. Can zoom in a little bit. What I'm going to do kind of first is just give a quick overview. So as part of the platform, you've got lists of pipelines. You have the executions themselves, which are runs. You have actions, which are automations, which you can set up here. And we also have Data Explorer and data sets, which I'll show you. The key to this, though, is it's driven from this concept of these computer environments, which you connect in. When you add those computer environments in, that's really making a connection between the platform itself and really where the execution is and where the data resides as well. Okay, we also have credential management here for managing those credentials, as well as secret management and participant management, so you can sort of control the access in that way as well. So I'm just going to do first a quick little demonstration of something which may be relevant for some folks. So I'm just going to go here first to SRA, and this is essentially a place where we can find access data. I'm going to do a search on this, and from that search, it's simply going to find for me a list of samples themselves. And from those samples there, I've got the survey. I'm going to basically select some samples in this case, and then what's that going to generate for me is a very basic file. And that file is just going to contain the actual file IDs themselves. So if I create that summary here, I could just define that and get the succession list in there. This has just created a file like local on my machine for that. But we can now start to integrate that with the datasets functionality that we have. So I'm going to go back now into the platform here. And from inside these datasets, you can see that we can very easily create a dataset. It's just simply that drag and drop here. You can add metadata. I've previously filled this out, so I didn't have to type this in, but you can see here I've created a data set, which is essentially a CSV file or TSV file of those accession IDs, which is kind of all good and well, but what can we do with this? We want to basically take some accessions and start to run a pipeline for that. So what I'm going to do now is go to the pipeline. We're going to use an NF core pipeline here called fetch-NGS, and this is the one that's able to take accession numbers, essentially IDs, and generate for us a sample sheet for it, and pull the files themselves. So when I'm going to launch this pipeline here, you can see there's a user interface for this, and all of the NF core pipelines use that parameters schema that's been mentioned a couple of times. to be able to build this. But now inside here, and this is a feature which is just from the last week or so, we can browse data in itself, but we can also have drop-downs. So we could say, let's say that we want to run RNA-seq after this. So it's going to create a sample sheet for us, which is going to match RNA-seq here. So I'm going to browse and find my data set that we had. So in this case here, we could start with the accession sheets that we had. So in this case here, the IDs. That's going to load that now. I could select the RNA-seq pipeline. I could choose where I'm going to download it. And it's essentially going to kick off here. And that's going to go spin up that pipeline up. I've got one I prepared earlier, though, so I can, if I jump into that, that might take a couple of minutes to run. From inside here, I can monitor that pipeline. So you can see under the hood, it's running Nextflow itself. You can see that we're pulling that fetch NGS pipeline. We have a history of the parameters, the configuration, any data sets that we've used there, as well as the full execution log for running that there. So we also get a kind of summary of the information as it launches through, and we get things like the aggregate statistics, and we can jump into the individual tasks, which I'll show you in a moment. So that's a kind of brief use case on how we would generate a sample sheet. And we're going to continue this example as we go through the rest of the presentation. Where are we going next, though, with pipelines? So we want to, as I said, be able to track these changes, particularly with regards to the details of the pipelines, making that like much more of an entity that you can share and use. We're also looking to improve the error handling. This is obviously feedback which is very much related to Nextflow itself. It can sometimes be a little bit difficult to understand exactly where the errors are taking place. In the cloud environment as well, when you're kicking a job off, it often takes some time, whether that's 30 seconds, a minute, 2 minutes, for it to actually fail. And that's obviously wasted time where you want to be able to do much more validation up front to get those errors to you earlier so folks can basically fix them in this way. We're also looking to be able to obviously collaborate on those pipelines and then really tighter integration with data. And it's that tighter integration with data, which is something we've been really focused on the last year or so in particular, and sort of something I'm very happy to announce today. Well, we released this as part of our public preview in Barcelona about a month ago, and now it's just been released into our latest enterprise release, which is this public preview of Data Explorer. Data Explorer allows you to visualize, search, and then manage data across different cloud environments. So if we give an overview of what it is, it essentially allows you to connect and access those data independent of where they are. So whether this is in different clouds, in different regions, in different accounts. And this is something that we see quite often where you want to have this kind of segregation of particular resources, but you still want a common interface to be accessing it in there. You also want to be able to link that data to pipelines. So when I've launched a pipeline, how can I figure out exactly where the data is, but also from the data, how can I go back to the pipeline? And this sort of starts to touch on some of the provenance things that we have coming up in the roadmap, as well as to be able to just basic browse, upload, download of files. The key is you don't really want your wet lab scientist to have to log into the console just to be able to upload a file into S3. So some kind of basic usage around that, as well as these public data set functionality, which is really kind of be able to have some sort of structure around what we call a data set here. So how does it work at the moment? It supports S3, Azure Blob Storage, as well as Google Cloud Storage. It essentially connects in with that. It uses the credentials that are in the workspace and just automatically uploads, or automatically, I should say, gives you access to those buckets based on those credentials, and as well as kind of providing that full access or full control from an admin perspective. So whatever credentials, whatever access the credentials have got, the admin has obviously got full control over how that works. So how can we see this in action? Well, we can imagine here that we've just finished our execution. In this case, the pipeline is run. Now we have the output of this, which we can see here is inside of this S3 path. So this is in this S3 bucket here, and what that pipeline generated for us is a sample sheet. And that sample sheet has got the sample IDs, the location of the actual file, so these are now on our bucket, as well as a whole bunch of other metadata associated there. So you can keep that information, that we can use this as a reference for later on. But where is this now? So what if I was not going from the pipeline side? What if I was going from here? I can use the Data Explorer now, and you can see here that inside of this I've got different cloud providers. So we go back, and then from there, also these are in different regions. So you can see here that we've got one which is in US East 1. You can see that we've got some Azure buckets, we've got some Google buckets as well, and we have the ability to go into here and just go through, browse onto this, as well as kind of jump into the actual underlying data itself. So inside of here, you can see that we've got kind of full browsing of the different projects. In case we've got different results, we can dive in and kind of go in that way. We can also do this from the workflow level. So this is particularly useful if you're debugging. If we go back to where we were launching the pipeline, inside of here, I can go like not inside of like the whole directory, but I can jump directly to where the results are, or even where the individual task work directory is. So very often when you're running a pipeline here, you kind of have this directory, you want to go check it out, you want to understand basically what's in there. Here you've got the ability to have the Data Explorer inside of that work directory. You can figure out exactly what the exit codes are, read those logs, etc., and jump in there. And this saves a significant amount of time in terms of having to jump to different contexts or use the command line, for example, to figure all of that out. Okay, how else can we use this? Imagine that we now have this CSV file. What about if we want to go launch the RNA-seq pipeline itself there? So I'm going to now go back to the launch pad. I'm going to find the RNA-seq pipeline itself. I can find that there. And here, when I'm launching this now, we can use now a data set which contains all of those samples themselves. So we've got this new functionality which allows us to browse here, either the Data Explorer, or it also allows me to browse, in this case, the data sets that we have. If we have a particular sample sheet that we've got that we generated from that, we can select that to launch that and kick off that pipeline as usual, kind of continue the process there. What about public data sets, though? What about accessing other things? So in here, you can see that we've got these different data sets that I've added in. But if I wanted to go, for example, and look at object storage here, this is the registry of open data on AWS. It's really just a bucket. And what we're seeing more and more is this trend towards really people relying on the bucket as almost like the default storage option. We saw it with examples like Parquet and some of the work that Edmund showed yesterday. This is just becoming the default way of doing things. And for us, that obviously fits very nicely with how we've been building things out. If I was to search here, it's for 1,000. And now I wanted to pull in, for example, this 1,000 genomes reanalysis with Dragon. Here I'm just going to copy the S3 path. And inside of here, I can simply add a cloud bucket. I can choose where the provider is. In this case, it's here. And I can simply say if it's public credentials, how that's going to act there. And now that's available for me in this environment here. So when I see this, I can browse this. So now I'm browsing public data directly inside of this. And I can now use that for the execution of a pipeline. So I can run a pipeline against that. But the real key is that this, for example, was in US West 2. Now, I don't want to go create an environment or run this in my US East 1 environment. But here, with Seqera, we can simply create a compute environment in that region so that we always run the execution where the data is. It's really about moving the workload to where the data is itself. And this kind of functionality provides a little bit more visibility on that and the ability to expand that as well. We can also do the same thing. In this case, we've got some broad references from Google. Very kind of similar story. You can link that in as well. Okay, going back to the roadmap for this. So when we think about what we're doing, we want to link more of the input and the output. I kind of showed you some of the new functionality that's happening there. We also want to support different data sources. So really doing a kind of call to object storage is just an API call. How can we expand this and to have that integration with SRA directly so that we don't have to switch context like I did at the very beginning there? How could we pull in things like benchling or base-based data directly into this interface? How can we also add in now support for shared file systems as well? So if people are doing this in HPC with Seqera, you can launch into those environments at the moment, but we want to provide support for file systems in there so you've got that same experience. as well as the data packaging and provenance piece as well. I think we're going to get a talk later on from Ernie as well, who's going to give us a little insight into some of the work that's been going on there with those integrations. So as I said, Data Explorer is now available today. You can try this out on Seqera Cloud, and is also now available in the enterprise release that we just had. Okay, so that was a lot on kind of the Data Explorer side of things, but what about the interaction? What about you want to take the output of that pipeline and start to interrogate it? Maybe you want to generate some figures. Maybe you want to do things in a much more interactive way. And this is what we've launched Data Studios. So Data Studios is launched as a private preview. As part of this, the idea is how you can launch those interactive environments, things like RStudio, Jupyter, VS Code, and thinking about them as they're, by definition, they're IDEs. But really they're kind of interactive scientific environments. And as we think about that, that's becoming such a common way to interact with things. We wanted to come up with a way to apply a Nextflow-like approach to that, which is run it anywhere, define it as a Git repository, and think a lot about the dependencies and how we can make that process simpler. We also want to connect this to pipelines. So whether this is debugging a pipeline, going directly into the work directory, be able to spin up an interactive environment there, as well as develop these kind of tools in a native environment. So when you're developing the pipeline in the same place where you're going to be running it with the same access to data and production, et cetera. So how does it work? Well, it's a container environment. So it essentially just launches a container wherever you can run Nextflow. We define the dependencies here via Conda or SPAC or Docker files on this, as well as go for this portability. So this idea that you can drop a Git repository in which defines that whole environment. And again, the access control is done through the credentials themselves. Okay. If I give a quick kind of look how this looks through. So this is the interface here for Data Studios. You can add a studio by simply selecting the template. This is essentially a container at the moment. You select the container, but I think the real key thing is now we can start to mount that public data, or the data that I have from the account, inside of the notebook. And this becomes really impressive if we look at, for example, an RStudio example we've launched up here. Here you can see that I can pull in the results of that pipeline that we previously ran. You can see here that we've got a TSV file inside of here. I can simply kind of see that. I can use that information. I can generate a plot from this. And again, this is kind of running in the same place that your Nextflow pipelines would run in there as well. Another example of kind of looking into this is with Jupyter. So here's an example. Just got to connect in here again. Here's an example here where I'm running that same data. So I've pulled that data from that pipeline. And let's give it a second. I'll pull that in. I'll jump through to VS Code while that loads there. Yeah. So when we think about not just in the experiment with sort of Jupyter, but what about how developing code? Like what about on developing pipelines themselves? So here's an example where I've done a Git clone of the RNA-seq pipeline, and now I can actually run Nextflow in this environment here. What I was mentioning before on the data side, here you can see that we're using, in this case, we're using Fusion to mount the, in this case, 1,000 genomes bucket inside of this environment, so I can develop and work on it directly. And we're going to explain a little bit more on how that works in a moment. Okay. So here's my Jupyter environment here. It's going to load it up. Show why it's really slow here. But as I mentioned before, here's the data, so you can access different object storage, which essentially can be pulled into that, can be drawn into there. If I look onto my notebook, sure, let's try and load that up again. Still don't want to load for me. In this example here, we're essentially going to take the results of that. We're going to feed that into OpenAI, and that's going to generate for us some code based specifically on the actual data. So it's like feeding in the data via the API there. And what this does is generates for us kind of some code, which is then going to take the existing data, create a series of figures for us specifically to be used in that. And just a kind of a quick example of a use case for doing this as well. Okay, roadmap for studios. So we really want to make this experience with regards to dependencies much easier. if we think about things like RStudio, you spend a lot of time installing modules, figuring them out. They're not exactly fully reproducible or easily reproducible in the same way that things have been done for Nextflow. I think the audience here is slightly different as well. Nextflow was able to capture a fair bit of market share or user share from relatively sophisticated users relative to all of the use cases which exist for interactive environments. So we want to be able to bring that, all the benefits that you get from containers and reproducibility and to those set of users, which is going to be definitely a different challenge, but I think that the technology is there now to be able to allow us to do that. We also obviously want to replicate that research environment, so that's the same thing on that reproducibility, as well as add more support for different major cloud environments as well. Feedback on this is going to be really key, so particularly as we think about what's the definition of that container environment. We're looking at things like dev containers, which seems to be a very good job of defining exactly what goes into that, but there's still work to be done here as well. Okay, there's a private preview of this as well, so if you want to access this, sign up for this and we'll let you know as soon as it's available. This will be available on Seqera Cloud. Cool, so just wrapping things up here, when we think about this, we now have really ways of being able to connect in, whether we're writing tools, developing pipelines, linking all the way through here. Still a lot to do, I think, particularly around the management of the data, but there's still there's kind of big strides that have been taken in the last year or so to drive things forward. I'd also just like to announce a couple of other things that folks may not be aware of. We have Seqera Cloud Essentials, so this is essentially a free product which you can use, which has access to pipelines, to Data Explorer, and Data Studios, kind of fully featured in this way. You can have up to 5 users onto there at no cost. And we also have an academic program, which gives you Seqera Cloud Professional at no cost as well for eligible academic institutions. So if you want to sign up for that, feel free to do that, and we'll get in contact with you. Likewise, we do have these multiple deployment options, so if you are keen to try things out, we recommend trying Seqera Cloud, and if you want to speak to us about enterprise, we'd be happy to sit down and do a bit more of a tailored deployment for you there as well. All right. With that, I'd like to thanks everyone for taking the time. I'm going to be around for the rest of the day, so here if you want to have a chat. We've also got a fair few other Seqera folks in the audience as well, so feel free to reach out to us if you've got any questions. Thanks so much.
All right, thank you so much for this overview, including demo. That's always an interesting gamble, but it worked out very well, I would say. Okay, so one question: can you put the slide with the QR code back on screen?
Yes.
Because a lot of people wanted to get a shot of that.
Which QR code? This one.
Yeah, that's the one. There you go. Popular vote. Okay, we have a number of questions for you of various levels of granularity. I'll try to get that. All right, first, yes. How do you keep track of the version of the data from Data Explorer used in the pipeline?
Yeah, good question. At the moment, we have data sets which has got different versioning, so you can create different versions of it. It's still not, it's not like a pure tracker of the actual contents of the file. Although Nextflow itself does have a caching mechanism, so Nextflow is going to do a checksum of that, so you're going to know if your data is different. It's something that we want to build in though more natively without having to launch pipeline.
Yeah, and data provenance is generally a big concern and challenge, so yeah. Are you building in auth-n, auth-z into Data Explorer integration with RAS, dbGaP, GA4GH passports, with the goal of allowing users to get access to controlled access data sets?
Yeah, we'd love to. We are looking at a lot of integrations at the moment on how to do that. Nothing concrete, but we'll have more news for that shortly.
All right. Still to do with Data Explorer, it's a very exciting topic. How does Data Explorer help with data localization, specifically in the case when you're trying to use data from multiple repositories, especially across clouds, in the same workflow/compute environment?
So Nextflow does a lot of heavy lifting here in terms of transfer of files. So it will take data and it will do that staging across for you. In terms of Data Explorer's current functionality, it's much more visibility. So upload, download, viewing, as opposed to actually doing any sort of heavy lifting moving there. But Nextflow does have that functionality. It's always one of these things that it's kind of user beware though, because obviously the time and the cost of moving data across clouds and across regions, it can be very expensive. So something we want to continue to raise the visibility of that so folks can know what they're doing and can be kind of sensible with that.
Yeah, and often this is kind of a question of engineering, setting things up so that some of the analysis can be done on pieces of data separately, and you want to keep that on their own regions and only bring things together in the same place when you absolutely have to.
Yeah, and bring your own cloud is really key there as well.
Yeah. Moving on to data studios, what costs will be associated with running data studios?
Yes, so currently the data studios, it just runs as a single container, and it runs that in this case on the AWS batch environment. So it's whatever costs are associated with running your batch environment there. In this case, I think that we're doing 2 CPUs and 8 gigs of memory. So it's very low overhead, probably very similar to the Nextflow head job.
And can the user configure that environment, the backing hardware?
Yeah, absolutely. So they can choose the container currently, number of CPUs, memory, obviously where the execution takes place, where the container is provisioned.
Still with data studios, if the RStudio sessions are running inside of containers, how do users install more libraries themselves inside RStudio and maintain those custom user-made environments inside the containers?
Great question, and that's something that we're looking to do now. When we think about what we can do with Wave, we can build containers on the fly. So we can select from, say, for example, from Bioconda, the packages that you want, and then be able to build that in a reproducible way. The challenge, though, is a bit of chicken and egg there, because if I'm developing something or if I'm working in an RStudio environment and I need a new package, then how can we capture that environment? At the moment, we can kind of freeze it, but it's still not a satisfactory answer to be able to say, okay, here's the Git repository, which now defines that new environment you've created. So closing that loop is something we're looking to do, and there's some approaches that we've got, but it's still a little bit early for that.
And ultimately, the holy grail is kind of to be able to, when you publish your paper, publish your analysis, be able to publish a container or some kind of artifact that encapsulates all of it so that you can really have perfect reproducibility.
Yeah, and then be able to run that interoperably.
Yeah, indeed. One more question related to pipelines. Can actions connect to multiple pipelines to orchestrate?
Yes, what we've seen people do there is there's like a pre-run and a post-run script, so you can use that to connect it in. We're looking to develop our actions quite significantly in the first half of next year, having things like cron jobs to be able to much more easily run custom code dependent on conditions of pipelines. So that's something that's going to be a big effort of development coming up.
And I believe we have Harshal giving a talk about automation on Seqera platform this afternoon.
Exactly. It's really interesting. So all of that environment that I showed you there is all defined as code in a Git repository. Harshal's going to talk a lot more about that and how we can kind of use that to leverage that, basically reproducibility, not just on the pipelines that you run, but also the whole environments that you create.
Well, thank you very much. With that, we're going to break for lunch. Thank you to all of our speakers from this morning. Can I have a round of applause for them? Thank you. And so now we'll break for lunch. It's in the same place that you had breakfast, for those of you who joined us for breakfast. If you don't know where it is, just follow the herd, or look for Seqera people in the lobby of the hotel. And we'll see you all back here at 2 p.m. Thank you.
Oh baby, I wanted you to be here inside my arms where the night goes down. Oh baby, I wanted you to be here when the sun comes up and the day goes by. you to be here. Inside my arms, where the night goes down. Oh baby, I wanted you to be here. When the sun comes up and the day goes by. to be here inside my arms where the night goes down. Oh baby, I wanted you to be here when the sun comes up and the day goes by.
Hey folks, how's it going? We're going to start in just a couple of minutes, so great time to, grab a little coffee, find a seat. If you haven't had a chance to grab some socks or a t-shirt, they're also over there. We'll get started in just a couple minutes. How's everyone doing? Excellent. Everyone got lunch? Everyone got coffee? Awesome. Well, we have a whole bunch of incredible sessions this afternoon as well. We're going to kick things off with Paolo giving a session on the Nextflow ecosystem. And just a reminder, we have stickers. We've got shirts over there in the corner. If you want to tweet or LinkedIn post or whatever people are doing today, we're using the Nextflow Summit hashtag, and we'll post that in the channel for the spelling. So without further ado, give things over to Paolo.
Thank you. Very excited to present this work here in Boston. First time that we organized this event here in the US. So first of all, thank you for joining. Very, very appreciate it. And also it's very important here for the community. This year we are celebrating 10 years since we made the project open source on GitHub. So it's a good opportunity to say thank you everybody used Nextflow, contributed to the code, contributed to documentation, or just use every day in their work. This is fantastic because without you, this project would not be possible. So thank you again. And also it's very fascinating thinking how this idea behind Nextflow managed to grow from a small research project into an academic institution to something much bigger that goes beyond the project itself, the company. There is a community of people developing pipeline, using this pipeline in production every day. There is a kind of movement about this technology, so they keep together these people together, yeah. And the idea behind the idea behind is to enable the deployment of this pipeline in a scalable and a portable manner in different infrastructure. It can be the local computer, the cloud, HPC, data center, and also to enable the collaboration for researchers, for scientists. But the ultimate goal is to allow the scientists to focus on their work. And we want to abstract away all the complexity to deploy this pipeline. GitHub repository, cloud, storage, there is a lot of things behind. And the main goal Nextflow to allow instead the scientists to focus on their job. The point that we are going forward, we are facing more and more challenges. We have more complex pipeline, more complex infrastructure, I don't know, think Kubernetes, different kind of storage. And to solve this problem, just single tool, a workflow engine like Nextflow is not enough anymore. This is why we are evolving the technology from a single tool to an ecosystem, or a stack, like Eva was mentioning this morning. A stack composed by many different components, in which each component focuses on a very specific problem. You can use even independently this component, but when you use them all together, you have the best experience for your pipeline. But in this presentation, I'm going to talk a few of them, particularly Fusion, Wave, and Nextflow. Starting with Fusion. Fusion is an optimized file system for Nextflow data pipeline. The point is why we need a special file system for Nextflow data pipelines, because the real challenge for this application is not compute. You have plenty of compute, just enough having a credit card, you can buy as much as compute you want, but the real point is this pipeline consume, ingest terabyte of data, produce terabyte of data. So if you don't have an efficient strategy to manage the data transfer, I/O, into this pipeline, you are just wasting money essentially. There are plenty of different file storage, file system, but the point that most of the time they were designed for legacy system, for HPC, it does not fit very well into this context, especially in the cloud. Tend to be expensive when they are efficient, or they tend to have a very static allocation, and then there is an extra burden that you need to maintain to operate the service. You have to maintain the service. So ideally, we would like to avoid to have this kind of storage. Instead, use the object storage, because the object storage is the storage for cloud-native application. The point is that object storage like S3 has a mismatch with the tool that we use in data pipelines, because object storage is based on HTTP request and HTTP interface. Instead, tools into data pipelines use just the standard POSIX file interface. So the point how we can combine these two work all together. This is what Fusion aims to do, is basically an adapter layer that make it possible to use object storage like a virtual file system. So instead of having to copy the file using AWS S3 command line tool to take your input data or whatever from the bucket, copying the container or where you're running your tool, and then running the tool and copy back the result, what we can do with Fusion is essentially to have a virtualization of the storage, so that when you want to access a file into a bucket, you have a virtual path that is /fusion/s3 and the bucket name, etc. So, and then your tool can natively access to the data over the object storage and read and write the data from there. So there is a simplification from the implementation point of view, so that also these pipelines are portable, because they don't depend anymore by specific cloud storage. But also there is a lot of optimization that can be done behind the scene to speed up the operation. This is the point of this architecture. Here there is a very basic scheme that shows how Nextflow running a data pipeline, launch the job, run very similarly into a container, and then also we operate this driver within the container. So it's not like other solution that is something in the host. each job runs its own driver. This allows us to optimize the execution and the transfer of the data between the job and the object storage. So this becomes the adapter layer, your job for with the local file system. We intercept the API call, transform into S3 operation. But there is a very important point. The other doing this interface, Fusion is able to use the compute node local stretch storage as a cache, optimize all the data operation. This is the key point of this technology. So being able to optimize data transfer using the local instance storage that ideally should be NVM or solid state disk because it's the fastest one. And also it's nice to observe that into this architecture that is perfectly distributed. They mean that all the data transferred up at the job level. So there is no a central bottleneck or a central point of failure. Nextflow just use native API to access the object storage, but at the same time, the job download the data. Each job download its own data from the object storage, upload there. So this scaled very well. And Fusion is implemented as a Fuse driver. Also, there are plenty of these other implementation out there. So you may wonder, okay, why I should use these? Well, the main reason is that because we have designed these exactly to work with Nextflow. It's not like S3FS or many other that exist already, both as open source technology or commercial software. So it's designed to work with Nextflow, work within the container, and then there is this caching mechanism that speed up all the operation. A nice thing of Fusion that also have the support for symbolic link over object storage. This seems a little thing, but have very interesting impact in the execution of Nextflow pipeline. I will show you the reason why. Finally, it's super easy to configure. We want to make it simple to operate. It was one of the main points. We don't want to operate other services. So to use this in your pipeline, you only need to add few configuration settings. The Nextflow configuration, you don't have to store anything because it's automatically added in the container in your pipeline. We want to make a benchmark to compare this technology with other implementation because we say there are many. We decided to compare their clone is a popular implementation Fuse driver for object storage, and also Amazon Mount Point that was introduced a few months ago that does something similar, but they have very different performance. We use FIO, that is a benchmarking tool for Linux, simulating different operation. Reading small files, reading big files, and writing sequential manner, random manner. When we operate in small files, like this example, 5 megabytes, they more or less have the same performance. These are megabytes per second, they measure the throughput, how fast they read the data. More or less, they have similar figure. Fusion 6,800 megabytes per second, error clone 80,900 megabytes per second, Mount Point 80,000 megabytes per second, more or less. So the fastest one, error clone, the Mount Point in Fusion. And more or less the same with random access. Here, what we observe, essentially, they are all very fast. But why? Essentially because behind the scene, there is the cache of operating system, and when you read this file, you are reading the file from the cache. You are not reading from S3, essentially. So this is why they are very fast in all cases. When we jump into the reading big file, we start to see a big difference. And this is a 100 megabyte file. It's very common in data pipelines. You know, with Fusion, we can read nearly 6,000 megabytes per second with error clone 85, Mount Point just 3. And then still, there is a huge difference also for random access. So why there is this big difference? Because now there is not anymore the effect of the cache of the operating system because you cannot keep 100 gigabyte file into the memory of the computer. But Fusion has this smart caching algorithm as a second level cache using the local scratch disk that speed up all the operations, something the other tools does not have. And we see also this important difference when we work writing data. So also here is very, very much faster compared to our clone. Mount Point even crashed, we didn't manage to measure. So the bottom line is that this tool designed to work with large data. This is very common data pipeline. This is what makes the difference compared to other solutions. We want to also to benchmark executing a real pipeline to see the difference, how does it perform. And essentially here, we run NF core RNA-seq pipeline with a test full profile that simulates a real-world data set, running with AWS batch using S3, Amazon FSx, a shared file system into the cloud, and Fusion. So the first case is the slowest one because, okay, it's the less efficient using just S3 AWS batch. And to run all the pipeline, it took more or less 800 CPU hours. Using FSx is much faster because there is not anymore all the overhead of moving the data from the bucket to the shared file system and the result again to the bucket. So there is quite an important overhead that is only for data transfer. So the data pipeline was basically twice faster, but the interesting thing that we can do the same with Fusion. So Fusion is fast as a shared file system like FSx, essentially even a bit faster. And there is a huge difference in the cost of the execution of the pipeline. Here we are reporting the cost both for compute, data transfer, I/O operation, and the storage for 1 month to keep the result for 1 month. So with S3, the cost was $124, much more with FSx, and using Fusion, only $69. And this, apart of this cheaper, can be also a bit puzzling because we are seeing the Fusion is just an adapter on top of S3. Why? It's cheaper than S3 itself. It should be the same, no? We need to think a bit more about this. We were surprised as well. And then we realized that the effect was by the use of symbolic link over object storage. Because using symbolic link, essentially, Nextflow, they duplicate all the copy of the data. Because when you run a task, and this task uses the same input file, basically you are duplicating each time that you run the task, the input file. Instead, with the symbolic link, you're just moving the link to the real data. So this dramatically reduces the amount of data produced by the pipeline, so you have a smaller cost. And we wanted to also compare this effect across different execution, different pipeline, and basically we observed that when we run, we compare the execution RNA-seq with just S3 and Fusion, we have 19% less data produced by the pipeline, with the scRNA-seq minus 32%, ADAC-seq 44% less. With SARIC, this is impressive. There is a difference, 61% less data produced by the pipeline. So the bottom line is that if you are not using Fusion with Amazon batch, you are throwing away money, essentially. And availability of this technology, this support all 3 major cloud storage, AWS S3, Google Storage, Azure Blob Storage. We consider the support for S3 production ready. We are still working on Google and Azure to make to better tune the performance to be comparable with the implementation that we have for S3. You can use both with Seqera platform or Nextflow command line tool. Just adding a few configuration settings. There is nothing magic to be done. And this is a very important component about the storage. And then the other important component which we are working into this ecosystem is Way, component for the provisioning container for data pipelines. So container are pillar in the execution on data pipelines. Nextflow has been one of the first tools using consistently container for the deployment and to make the pipeline replicable and reproducible. The point is that in the last 10 years, changed a lot how we create container and how we write pipelines. So pipelines are much more complex. They use many more containers. There is this pattern to have one container for each task in your pipeline. So the early days was just one container with all the tools. Now we have many more containers. Maintaining all these container images is quite a lot of work. It's complicated to create, to build, to assemble, to deploy in different cloud. You have different authentication systems. So it's a lot of work. And instead, what we want to do is to remove all this work. So the core idea of Way is to to think container not like a static asset that is built ahead of the pipeline, but something that can be created dynamically, just in time, during the pipeline execution, so that we can optimize the container exactly for the dependencies that are needed for your task and for the platform in which you want to deploy the pipeline execution, so that you can optimize maybe for a specific CPU architecture. And also we want to make the container more declarative in the meaning that we want to say what the container should include and not how to build the container. I don't want to spend time writing the Docker file. This is ugly. And this is basically a schema of the main component. This architecture, this Nextflow running, launching the pipeline jobs using container. And then when you need to launch a container job, ask to waive the provision of a container, saying, okay, this container needs this tool, use this CPU architecture, this is the user, so can use the information about the user to authenticate the access to private container, and then decide to assemble the container using your Conda packages or the Spark package manager, and then send back, basically upload the container to a container registry. So essentially, Wave implement the API or container registry, but it's not hosting images. It's just behaving like a proxy or broker, and all the images are in the registry that you specify in the configuration file of your pipeline. What's new into this project? There are plenty of new features that we implemented in the last year, what we call container threads, the support for singularity containers. There is the security scan when the images are built. There is a command line tool. But I would like to focus on 2 points. This idea of the support for multiple architecture and optimization of the container. And so all the point here is to make it possible to be able to deploy the data pipelines, not just across different platforms, that can be local computer, the cloud, HPC, but also different CPU architecture. Now there is the emergence of the ARM64 CPU architecture, so what we use in the Mac computer or maybe AWS Graviton. But to be able to use this CPU architecture that provide more cost-efficient computing capacity, you need to recreate all the pipeline, all the containers for your pipeline, because they need to be built for that CPU architecture. And when you have 100 containers, it's not so simple to rebuild all these containers when you want to run this pipeline in this CPU architecture. And so the idea here is that we can do this on demand, matching Wave with a package manager like Conda. This morning we'll say that this Conda is rubbish. Well, not so much. Maybe the experience is a bit disappointing when you use in the local computer. It tends to be slow, maybe there is errors, but when you use into the cloud, like we are doing with Wave, with a stable environment, it's much better, it's very fast. So here, basically, we can deliver the container for the pipeline, depending on the CPU architecture, where just using the declaration, the Conda packages into your pipeline. And the second point is that also to make it possible to better optimize the container for a specific CPU architecture. This is why we added also the support for Spark package manager. Spark is similar to Conda, but provides an extra capability. Allows you to compile a tool, not just for a CPU family that can be Intel or ARM64, but for a very specific instruction set. So this makes it possible to even optimize the container and the tool for a very specific architecture that can be Intel, Skylake, Ashwell, etc. And if you're wondering how much you can gain from this, there is this interesting research paper that shows that you can gain basically twice the performance compiling a container and the tool for a very specific instruction set compared to a generic CPU family. Okay, since there are so many things, I think it's simpler that I show in practice how does it work, this technology. And you can download the command line that I was mentioning to you before from the Wave GitHub repository. Here there are different releases. They are pre-built for Linux, Mac, and even Windows, so you can use any computer. And I have installed here basically This is the Wave command line. This, when you run Wave, give you some example of what you can do, but essentially what you can do with Wave to access a container through Wave. Basically, I could just use Ubuntu. And it is Wave tells you this is the name of the container that you can use with Docker on other runtime to pull, for example, the Ubuntu container using Wave. So I could do Docker pull this guy. Oops, I need to specify the name. And okay, this is nothing magic. There is not a real gain doing this instead of doing Docker pull Ubuntu, unless using Wave can be useful to authenticate the access to a private container registry using the credential for the container that you can have in the Seqera platform. So Wave basically is able to authenticate your user, authenticate also the container that the pipeline will use when you launch the Nextflow execution. But the most interesting thing is that maybe you have a container and you want to modify the container with some script or some extra content that you may need during the pipeline execution for a specific job into your pipeline execution. Let's say that you have a directory, this is my script, and here we create a script that is my script hello sh, and then I do maybe a bit bigger echo hello submit Boston. And then as like this, I give execute permission, my script hello. Okay, now if I want to use this script within the container, sure, I build the container, the usual flow, but I can do something that's faster using Wave -i for image. We said we want to use Ubuntu, and then I can specify layer to say I want to add this container a new layer, a new content that essentially is this directory that I created here. So everything that is into this directory can be made accessible to the container using this command. Then I could run this container, taking this, and then sh-c /hello to log. Let's do this. .sh. Pulling the container and then running the script into the container. So here, the important thing to realize that this was not a build. The data that I specified with this command line option is added on demand while the container is pulled. So why this should be better compared to a normal build? Because imagine that your pipeline, you have 10 different containers or 50 different containers, and all of them need a special piece of software, a script or whatever. Instead of rebuilding all of these manually or with some sophisticated CI script, we can automatically augment a new layer in the container via Nextflow using this command line tool. And this is an idea. It is exactly what we are doing with Fusion. So how we make it possible to use the Fusion file system into your pipeline without changing the container using this approach. Essentially, Fusion is appended to your container into the dynamically in this way. But yes, if you want, Wave can also build a container. I can use the usual Docker file, say, from Ubuntu. I want to add the same script, hello.sh. I want to put user lockup bin hello.sh, and then I want to execute automatically. Okay, done. Now, how to build a container with Wave using Wave -f file, and then specify the Docker file. I need to specify also here, not the layer, but the context, more or less the same thing. This is always the same directory, my script. And okay, now I have, again, a new container name, and now Wave is building this remotely in the cloud, in the Wave cloud, the Seqera cloud. And then I can pull, like, let's do this alias d equals Docker d run this guy. and voila. And we have the container built, ready to run, and we can run this way. Also, we got notification when there is a build operation. This is the notification that is sent by the system. We can say the container metadata, the ID, the user, the IP, where is physically stored, some other things, the container file, the log of the build, and also the link up to a scan operation that's been done against the container to see the vulnerability. Here, there could be something that maybe we should fix. And so, basically, we can both modify dynamically container, but build container with a Docker file, but we say that if we don't want to use Docker file with container, we want to create container dynamically, not dynamically, in a declarative manner, and immediately using Conda packages or Spark packages. So how to create a Conda-based container with Wave? You can say Conda package, and you have access all the Conda collection. So here I could say I want to use BadTools 230. And we go. We have a container with BadTools. Docker run BadTools version. Pulling the container that's been built on demand and running it. And you may think, okay, this is nice, but why I should use this? Because for each Bioconda package, it exists already a Bioconda container. Well, that's true, but only for Bioconda. Conda is much bigger. There are many more channels, and does not exist container for other recipe in Conda. But above all, for one more interesting thing, with biocontainers, you have one-to-one mapping, one-to-one container. What if you want to use two tools into the same task? You don't have the container anymore. Instead, with this system, you can do Conda package and create a container with all the tools that you may need into a task. Package. Oops. It's not simple to type into this thing. Some tools, 170. And again, so basically we have another container that contains two tools. You can add all the Conda package that you want to use in this system. Docker run, these guys, some tools, version. You can do the same using Spark packages, even though we consider still experimental. And so with this mechanism, we have much greater flexibility. This takes a bit time because now it's built the reality, the container behind the scenes. So when it's going to be ready, we start the pull. Maybe. Okay, need a bit more time. Anyhow, while we wait this, another interesting thing that we can do other than building container with different packages or augmenting container. Oh, finally. This is Conda, this is slow. Some tools, maybe I specify something different here. Some tools. Okay, I don't know. Now I don't want to spend more time understanding why it's not giving this error. But the nice thing that apart this, okay. And what if we want to instead create a container, not for Intel, but for Graviton, for ARM64? The same, I can use the same command and specify platform, Linux ARM64. Essentially, we are doing the same, but specifying a specific CPU architecture. Again, we can create a container for this CPU architecture. So now, if I run this, it should not work because this is an Intel VM. It cannot run an ARM container. And it says except format error. But this shows how simple it is to switch from one platform to another. And one thing that also was mentioned before is the idea of the Fritz container. What is Fritz container? You have noticed that every time that we run Wave, it gives us a slightly different name for the same container. If I repeat this, one more time, you see that there is this part that changed. This number represents the checksum of the container. That does not change over time. Instead, this component is a unique identity token that allows to make the container accessible for a short period of time. This is an authentication system, essentially. The problem is that using this mechanism, you can access, you don't need anymore to have the login, the container registry, but you have this name that is ephemeral, change all the time. And for some customers say, okay, but I want more predictable, stable name for the container. And this is why we introduced this idea of the freeze container that allows to create the container with Wave and upload to your container repository in a stable manner somehow. So when you use freeze, you have to specify the build repository, and you want to upload this in your own repository. It can be Docker. In my case, I want to use my own Wave demo. The difference now that I have a stable name. This is the name of this Wave container, and every time that I can try to re-execute, I get always the same container name because there is no change. So there is a caching behind the scene that keeps track of this. So these are the idea of the container feeds. And another interesting thing, we said we can build container for different platforms using different packages, but also for different container runtime. Singularity is very popular in HPC, but is used its own container file format. So if you want to build container for Singularity, it's a different experience, but with Wave, you can just say Singularity, maybe, and then we have a container that is for Singularity. If you remember, if you have used Singularity, you remember that Singularity uses not a remote container usually, but a file that is the Singularity container. So how we can use this approach with Wave is a registry. Because also Singularity, you can upload the Singularity file into OCI registry. You cannot run with Docker, but still Singularity they can pull and push from there. So exactly what is happening now. If you notice, the only difference here is that there is this prefix here that Singularity knows how to use, how to interpreter, and I can say Singularity exec, this container, and again, but tools version. So basically, now, okay, I have already cached this, so but basically, it's cached then locally, and you can run like any other container. So it's super flexible. You have very many different ways to assemble provision container for different platforms, CPU architecture, container runtime, and whatever. The point is that how to use this with Nextflow. You are not expected to use the Wave command line tool. This is perfectly integrated into a Nextflow pipeline. So to use this is enough to specify that you want to use Wave into Nextflow configuration file. And we also added a new command to Nextflow to make the experience more transparent, otherwise it can be a bit confusing. There is the Nextflow inspect command that allows you to inspect all the container used into a pipeline. For example, if I type RNA-seq-NF, this is a small pipeline that we use for demoing, this by default use one container for all the pipeline execution. You will see they use this container and it is on key, RNA-seq-NF 121 for all the tasks. But what if I want to use now Wave with Nextflow? It's enough that I edit my Nextflow config file, I enable Wave.enable true, and then I want to use this approach, this pattern, to build the container using the conda package associated with each task into my workflow. So I say Wave strategy equals conda. And this is enough to tell Nextflow to use Wave, as I was showing you before. Now, if I run Nextflow inspect for this pipeline, I take this configuration file and invoke the Wave service, and now I have the Wave containers into my pipeline execution. I could run and use this container. What to use the freeze container? Just say Wave freeze true and Wave build repository Docker IO with demo. Okay, like before, I can run it again. And now it does the same, but it uses these phrased containers that are in your own container repository. Now, docker.io, Salmon for these two steps, multi-QC for multi-QC step, and fastQC for the fastQC step. If you are not getting the link between the container and the pipeline, it's enough to just take this pipeline source code that is here, and you can go in the module, and each module declare the Conda package. So we've used this declaration to decide how to assemble the container. And okay, maybe the last thing, if I want to do the same with Singularity, you may have Singularity enabled. Singularity, it's complicated, it's word. Enable into your pipeline. And when I run the same thing, I have the same container built for Singularity. And okay, so these are the main capability on this on Wave Container Provisioning Service. So change a bit the way the flexibility that we have to assemble the container in our data pipeline. And we are making this available as a version 1.0. We are operating for more than 1 year, and the last year served more than 1 million containers requests, so we consider stable enough to go in production. Also, a very nice thing that we are also making available as an open source software, so other the command line, also the Wave backend is accessible in this GitHub repository. You can go there, download, play with it, modify the code, make contribution if you want. Also for people that are interested to use on-prem, we are also making available as an enterprise distribution starting from next year. So there are many different ways you can use this software. Okay, and then the last part, Nextflow. Nextflow is the pillar of this technology, this stack. The last year, all the work now, but part of the work was focused to smooth the interoperability across the stack. So between Wave and Fusion was the main theme, is the main theme of the version 23.10 that we make available the past month. So not surprisingly, now we have the support into Nextflow also for Spark Package Manager for the reason that I was mentioning before. Now there is a new directive that is Spark that you can use like somehow Conda to declare the dependencies for the task into your pipeline. And again, this can be used to build the tool locally or using Wave. Along the same manner, we add also the support for the architecture directive. Now into your pipeline task, you specify pure architecture and also the microarchitecture like this. And this is used mainly by Spark in conjunction with Wave to target very specific CPU architecture when you want to run your pipeline. Then also, Fusion is first-class support file system into Nextflow pipeline. It's supported by the cloud executor, AWS Batch, Azure Batch, Google Batch, but also other executors like Kubernetes. And this also, especially with Kubernetes, Fusion simplify a lot the deployment Nextflow pipeline into this cluster. You can even use Fusion with local executor. So you can run your pipeline in your computer, use S3 as the scratch word there for the pipeline. This is maybe is not super efficient, but makes sense maybe if you use EC2 virtual machine to scale the pipeline vertically. If you launch a solid virtual machine, you can use just single node scale in this manner without caring about the local ABS disk. Finally, there is also the support for Fusion for Slurm, LSF, a Green Engine Batch scheduler. It is also open an interesting chapter because allow to use the distributed file system, or this virtual file system on top object storage with HPC batch scheduler. And of course, here make more sense not to use cloud storage, maybe unless we are using a parallel cluster that was showed this morning. But if you are operating Slurm or on other keys, HPC on-prem, you can use a S3-like object storage, like manual or Ceph, to move all the scratch or the pipeline into the object storage. I think this is a very interesting solution. Few small things that are new instead, not into the 2310 release, but the latest Edge release of this month, 2311, is the support of Singularity OCI mode. Again, container, we say the container are important. Now Singularity has a new feature, the ability to run natively Docker container. So it's not needed anymore to convert a Docker container to the Singularity image format, can run directly. And to support this, you need to add a configuration option into the Nextflow configuration file. And this is, I think, very interesting because reduce the need to create container specifically for Singularity, so increase the interoperability of container for our pipelines. Another nice addition that we adding to Nextflow, what we call topic channels. If you have used Nextflow, you may remember there are mainly two types of channels, what we call value channel. This is a kind of channel, essentially you can associate a single value, and then the other task can only read that value. And then we have the queue channel, that is one point-to-point communication channel for one task that produces some data is sent to another task. Now we are adding a new type of channel that is topic that is more like a broadcasting system. So the idea is that you have a shared channel to which many tasks can write and many tasks can read. This can be useful to implement some specific pattern. The main reason came from the NF core pipeline, in which there is this need to collect the version on each tool, and there was this continuous concatenation of channel over channel over channel to create a big channel containing the data coming from all the processes. This can be solved instead in a much more elegant manner using this idea of the topic, where many processes like this, now there are only two here, but basically this is showing that I have an output, the tool version I send over the topic version, and another task, or more than two, can do the same. Always, this file is sent over the same topic. And at some point in your pipeline, you can reference the topic by the name and can be used like any other channel with an operator or into a process to collect all the data came from these processes. And another extension that we are adding to Nextflow, what we call the command output type. This is always somehow related to this problem that there is in the NF core pipeline to collect always the version of the tool in each process. If you notice that there is always this boilerplate at the end, the bottom of the task, that is needed essentially to run the tool with the version to capture this metadata, and then is sent out like I was telling you before. And this is doable, but it's a bit ugly because I have a lot of noise into this task. I would like to see only the real command into this task. So instead of doing this, what we can do now, the upcoming version, is declare the command that they want to execute like a new type, that is CMD. This run on the fly, the command, capture the output, and then we can use like we were doing before. And okay, quick overview roadmap for next year. There are really a lot of things on which we're working on, but I would like to focus on what we call for DSL3. DSL3 is not going to be a new version of Nextflow of the language, but it's more the idea, not the idea, the need to have a better experience for Nextflow developer. The overall idea is to have a static type language instead of a dynamic type of language like it is now, that make very difficult to have a proper error reporting system or to be able to detect syntax error into the pipeline execution. You can discover this only during the pipeline execution. Instead, we want to make this experience much more static oriented so that the Nextflow, when you launch a compiler pipeline, the parser can identify all the problem and provide much better error reporting. And also having a much better ID experience. So while you are typing your pipeline code in VS Code or maybe IntelliJ, the environment can automatically suggest, okay, you can do this, you can use this operator, maybe can highlight the error, and so on. So they're planning to have much better developer experience writing the code for Nextflow pipeline. That's it. I hope that you enjoyed this presentation. The idea of Nextflow, it is the idea to evolve Nextflow from a workflow engine to an ecosystem of different component tools, always keeping the original vision in mind, so to make it possible to remove all the complexity and to allow the scientists to focus on their work. Thanks a lot for your attention. Also, a few seconds to say thank you, all the fantastic team working into this project. Thanks again.
Awesome. So we don't really have any questions in Slack. There's one that I think is probably a little bit nuanced, and we'll keep in Slack. We're running a little bit late, so I think we'll call Catherine up onto the stage, and she's going to be talking today about event-based integration for pipelines. So with that, please welcome Catherine to the stage. Thanks.
Hi, I'm Catherine. I'm a bioinformatics analyst at the Englander Institute for Precision Medicine at Weill Cornell Medicine, and I'm here today to talk to you about event-driven solutions to integrate pipeline executions within a complex informatics infrastructure. So, Nextflow pipelines are usually part of a larger informatics ecosystem. The problem is, linking these systems together is difficult. So, manual intervention is often error-prone and slow. There are delays in reacting to completed pipelines and errors. Like, for example, I had a pipeline end at 2 a.m. on Thanksgiving this past week. And many software solutions to this are strongly coupled together in that they are proprietary, part of one package, not necessarily easily extensible. So here's the core of what I do. So I do bulk RNA-seq mostly. So I have raw data. I put it into our laboratory inventory management system just to record everything. I use that to generate a sample sheet, feed it into Nextflow. Nextflow feeds the jobs into my executor of choice, and I get some results out. But really, this is only part of the picture. So with these results, it's part of a larger ecosystem. So these results go into CBioPortal. They could go into a clinical report that updates electronic health records, maybe a Jupyter notebook or a Shiny app, and of course I have to put them back into LIMS too. So really, automating sample sheet from LIMS, not too bad. There's guides on Seqera blog to automate Nextflow start with Tower. Nextflow manages all the jobs, but all this stuff in red is often a manual step. So what's the solution to this? So really, we want to automate communication and actions between all these pipelines and other software components. So ideally, the solution is generic, it's built around Nextflow, and it needs to work on a variety of HPC and cloud platforms. You have Slurm, you have Google Cloud, you have Azure, you have AWS. There's a huge variety out there. So really, our answer is to move to an event-driven architecture. So first off, what is an event? So simply put, it's a change in state. You have a new file. You have a pipeline starting. And this is wrapped in a message with a description of what occurs. So we can conceive of a pipeline as a series of events that you have a sub-workflow. You have tasks, beginning and ending. You have errors, of course. I personally forget to allocate memory all the time. And of course, there's workflow completion, whether that is successful or an error. So the question becomes, how do we track, discover, and react to these events? So our solution is based on Apache Kafka. So it's an open source platform maintained by the Apache Software Foundation, written in Java, and it facilitates communication through a Kafka broker. This broker organizes message logs into topics. Services can publish a message to a topic, and other services subscribe to topics to listen to these messages. So, what we are presenting is the dispatcher suite, which has the main feature of the Kafka dispatcher. Simply put, a Kafka dispatcher is an interface to a Kafka broker with a single point of configuration. You give it a YAML file, and it will listen to your topics, send messages to topics. So it's a Dockerized microservice. And again, it can publish messages, and it can subscribe to topics to listen to messages. So what's special about it, too, is that it can trigger actions based on those message contents. Again, just specified through your YAML file. So this could be a simple API call to, again, a database. It could just be whatever bash command you want. And of course, you could do Nextflow run, EIPM RNA-seq, or even tower launch. So how is this implemented? What does this look like on a basic level? So here's just a simple image. So I have a dispatcher, a Kafka dispatcher associated with LIMS, my inventory. I have a Kafka broker, in this case with 3 topics, start, progress, and complete. And I have a dispatcher associated with Nextflow, my job submit node with Nextflow. So the dispatcher responds to an event in my LIMS. So in this case, it could be creating a sample sheet because there's enough data to create a sample sheet. So the dispatcher can send a message containing the address of the sample sheet to the topic start. My other dispatcher on the job submit node is subscribed to this topic start and can trigger an action based on the content. So I give it, there's a message with the sample sheet address. The dispatcher gets the sample sheet address and can trigger Nextflow to start my pipeline. So this isn't too bad so far. There's plenty of ways to automatically start Nextflow, but what's special about this, we want to think about integrating with Nextflow itself. So we created a little library, ZeroMess. It's a lightweight, groovy library for interacting specifically with our Kafka dispatcher. So this is a jar that you drop into the lib directory, and it's used by both the main Nextflow process and each task on your nodes. So this enables publishing messages for your workflow events. So pipeline start and end. So the onComplete handler is a miracle. Your task start and end. So you have a task start up. You can see a message for that. Any critical errors that happen, again, on error handler, very handy. And any other debug or log information you need. So I have another diagram for you. So we have our analytical environment. This could be, again, AWS, Google Cloud, like any HPC. We have a job submit node with Nextflow with access to the ZeroMess library and a Kafka dispatcher. We have a broker. This time I haven't shown the topics, but we have tested this with on-prem Kafka, event hubs, and AWS MSK. And of course, we have other systems available with Kafka dispatchers. So Nextflow, as we know, submits jobs to a node. The nodes can use ZeroMess to interact with the dispatcher on your job submit node. So this dispatcher sends messages which are received by other dispatchers, again, facilitated through a broker, like such as event hubs or MSK, and we can trigger actions. So again, in this case, I may update a database once my alignment is done. I could have multi-QC running, and once the process is done, I can get an email saying, oh, hey, your QC is ready. So when the pipeline is done, I get a Nextflow itself, your main workflow, can use the ZeroMess library to send a message to the Kafka dispatcher, again, facilitated by the broker, and other systems can handle the message and react to it. So in this case, again, you have an email, you could have a dispatcher sending emails, but it could send multiple emails. It could send it to your HPC administrator on the case of an error. It could send it to a PI, that person in your lab that knows all the Nextflow, whoever you need. So, and again, you can collect, run metadata, and update another database with that. So, what is it that we can do with this framework? So I've already described a little bit of what we can do. So one major example is we can start pipelines automatically with accumulated data. So watch a database, or watch your S3 bucket, see some data show up, create a sample sheet, send it into, send a message with the sample sheet address. So again, as tasks are done, you can update LIMS or an electronic health record with any information, like, again, have an alignment, put it into our bioinformatics table on LIMS, because that's how we track all our files. We can contact multiple stakeholders on a pipeline failure. So again, that person in your lab that knows all the Nextflow, they can help you out. So CBio Portal is a part of how we at EIPM share data. So we could have data from our pipeline added directly into CBio Portal. And really, one exciting thing is that you can chain together complex pipelines on that on-complete message. So I remember watching the Barcelona Summit live stream, and there was somebody presenting the genomic imputation pipeline. There was a question about combining it with Saric because it could use BAMs from Saric as the input. So rather than combining two highly complex pipelines, you can chain them together. Another simple example, NF-core, BAM to FASTQ into RNA-seq. Not too bad. But again, you can chain together these highly complex pipelines rather than just have them all in one hard-to-maintain program. So in adding additional systems is very easy. The Kafka dispatcher is just a little Docker image. Just throw it up. First time I did it took less than an hour to learn how to configure it. So it's very simple. So what's the roadmap here? So one thing I do want to say is that this system is more than theoretical. It is in use by our clinical genomics lab for TSO 500. And we plan on releasing the Kafka dispatcher as open source software within the next year. And really, we are going to create a plugin, NF Events, to publish events in Nextflow. Initially, it will be a wrapper around our ZeroMess library and able to communicate with that Kafka dispatcher directly. But in the future, we want to be able to publish messages directly from Nextflow without interfacing with that without the dispatcher. So I was a little fast, but here's some acknowledgments. So of course, all my co-authors like Manuel and Andrea and I have put in a lot of work. That picture, it's me on the left, Andrea, and then two members of our comp team, Pooja and Peter. There's also Noah, Sean, Zichan, Zhao Fei. You know, and then I want to say hi to my office mate, Mai. There's Alicia, there's Mike, Jenna, Jyoti, and a lot of people at EIPM. So there are some code examples. Again, the Kafka dispatcher is now open source, but these are some examples of how to use messaging in a pipeline. So Hello Mess is a simple pipeline Manuel wrote to demonstrate the different types of messages that can be sent. And RNA-seq messaging is a pipeline I wrote, just a little stub, to show how messages might look in production. So, all right, I'm happy to take any questions, and thank you so much for having me.
Awesome. So I think we've got two quick questions, maybe. Okay. First question, have you explored SQS or SNS instead of Kafka?
No. So Kafka, you know, we're using Spring Boot and Spring Kafka to interface with things. So that was, you know, Manuel was the one that wrote most of the code, Java developer. Really, it was the best solution for us, Apache Kafka. So.
Awesome, thank you. And second question, have you thought about porting ZeroMess into a Nextflow plugin?
Yes, that was, yeah, so we do plan on doing that. Again, we are looking to name it NF Events. Again, initially NF Events. We'll be able to interact with the dispatcher, but in the future, our hope is to have it send messages directly to a broker. So, yeah.
Awesome. Well, thank you very much for answering those questions. Give a hand for Catherine.
Thank you so much.
And then coming up next, we have Zahab with a presentation on moving from pandemic response to preparedness. Give it up.
thank you very much. As introduced, my name is Zohaib. I'm a postdoc at the Center for Infectious Disease Genomics and One Health at the Simon Fraser University in Vancouver, Canada. The title is a bit of a mouthful, so I'm just going to say the gist of it is that I'm going to present to you a framework which we have been developing over the last 2 years for the COVID-19 pandemic response, and how Nextflow is enabling us to go further into pandemic preparedness, being more pathogen agnostic. So let me see if I can use this laser. Yeah, okay, great. So I'd like to start with emphasizing that this is, I'm presenting here as a project leader, but this frameworks like these takes a village to build, and I have so many people to thank. Starting with my lab members, my advisor, I would like to highlight two until recently master students, Ivan and Madeline, who have been really instrumental in developing the front end and the data standards with me. And then I'd also like to thank people from the COVARNet, which is the Coronavirus Rapid Response Network in Canada. There's a subgroup, Cameo, and Paul, especially, who's been spearheading the functional annotation part, which I'm going to talk about shortly. And finally, last but not least, most important part was our collaboration that we early on wanted to establish with the Public Health Agency of Canada, and Gary, who's the chief bioinformatician there, who's been really a huge support in terms of not only giving us the vision, helping us how the public health labs want this data to be summarized. So that's been a great collaboration. And with that, I'd like to start with a bit of a story. Everything starts with a story, right? So this is 2 years ago when COVID-19 surveillance ecosystem, we've seen a lot of tools. This is kind of a figure that you might have seen, even if you're not working in the same ecosystem, you have probably seen in media. This is the next strain, very famous phylogeny-based, looking at how the SARS-CoV-2 evolves around the world. There's also a version of, similar version of it, I shouldn't say the version, but it's a CoVizu, another tool developed from the Cameo group. Then there are more mutation-specific tools, something like COV Spectrum and COV Empty, and also very well-known Outbreak.info that contains all these mutations, variants, and some metadata attached to it. So what we thought was there was a bit of a gap where the link between these mutations and its functional significance was missing. So specifically in SARS-CoV-2 surveillance. So what we wanted to fill this gap was have a tool that would be interactive visualization and overlay the functional significance of each mutation so that you can understand which mutation is having an impact and what are those mutations that are common between different variants, but have a significant impact on the, so to say, the biology of virus, really. So the goal, as I mentioned, was interactive heat map-centric visualization that combines genetic mutations, lineage information, and the curated functional integration, which is the key to study the evolution of COVID-19. So we believe that by overlaying this information, one can understand the impact of that mutation in terms of transmissibility of the disease, disease severity, immune escape, and other pharmaceutical effectiveness. So we came up with this structure, which is really 3 standalone components: a front-end visualization, functional annotation, which is manually curated, and a genomics workflow, which is where Nextflow comes in. So the front end is written in Dash and Plotly frameworks, but I want to highlight this function annotation component, which is really an important part, because what we've been trying to do over the last 2 years is to scan the literature through various sources, including PubMed and bioRxiv and all these different resources, government dashboards, even social media commentary, because I think even though it's very difficult to standardize that, but it is one of the most important and really helpful resources that people have been tweeting about different variants and mutations, and we've been trying to keep track of that. We developed early on a curation guideline for our curators to work on and curate all the information that is coming in, and then put into a flat file-based database. The front-end visualization would then view that, but also then the back-end genomics workflow, which is where I was leading, is to develop this NF core-based tools and also some Nextflow written custom tools to develop a more structure where we had one workflow. We named it as COVID MVP. So this was at the time called COVID MVP. MVP stands for mutations, variants, and prevalence, as much as I just want to keep MVP itself. And there are 3 sub-workflows at the start of it with 30 plus modules that were handling this data to process a population level study and then produce all those mutations into visualization. So in order to give you the essence of what the genomics workflow was doing, I think it's important to show the value of the data, how we package it, how we process it. So to first start with the front-end visualization, this is what most of the people are interacting with. So this is a bit of a heat map that gives you access to a lot of these features that we are processing in the backend genomics workflow and then keeping it as a packets. So you can see some key features like all the sequences that are coming out are grouped by lineages and the variants, classified them on the y-axis. You also get the number of sequences on the other side of the y-axis. There's this is more like scrolling back and front. You can see all the nucleotide position and the corresponding amino acid position. And the most important bit is right here. When you hover over a specific cell, which is right here, the mutation, you can see the mutation name, the reference and alternate allele, and also the functions that are associated with that mutation, which was the key what we wanted to achieve in order to have this exploratory analysis, exploratory tool that gives you immediate idea of what mutations are increasing over the time in a certain lineage and what kind of impact they're having. Then we kept on, more engineering, adding more features like similar color framework that Nextflow has for easier interaction with for the users. Then we had the idea of uploading directly a FASTA sequence that would contain a consensus sequence or a genome to process it and visualize inside your already available sequences. We also added a function for surveillance reports that are downloadable. So this is a bit of an animation of how this tool works. I didn't want to do a live demo. I'm not that brave, so I'm just going to do it as a animation. So you've got a search index built in. You can search a specific mutation, and the heat map scroll to that specific mutation. For example, in this case, the R3460, you can see all the variants that have that specific mutation. Hover over, you can see what kind of function they're attached with, associated to, and then there's, once you click it, then you see the literature attached to it, which is also key because we want to keep the evidence source inside this heat map as well. Once you click the cell, you get all the publications and the evidence source that are attached to it. And then you download the surveillance reports, as you can see, into a zip folder. Okay, so with that as a visualization, keeping that in mind, the next part was this function annotation. So it was called as POKE. The structure of that plat files is that we keep every single file named by a gene or a protein name and then a functional category. Then keep, if you look into one of them, for example, you can see there's a, probably not that well on the screen, but there's a chunk for each mutation where you get your functional description, a very specific function that we have extracted out that from the evidence, be it a publication or from the dashboards. And then the source itself could be a DOI, a URL, or it's mostly the URL link, and then the mutation, one or many mutations. So in several cases, there are multiple mutations that are associated to the same function, so they are just delimited by a semicolon to highlight that there are multiple mutations that in this study. And this goes on for all genes and proteins for SARS-CoV-2, and then different functional categories. To summarize this, currently we have 5 high-level phenotypes or the categories, which are medicine, cellular and molecular as an example, and then subcategories of functions could be pharmaceutical effectiveness, it could be tissue-specific neutralization, and all those different subcategories. And we have multiple evidence types that I mentioned, peer-reviewed publications, preprints, case studies, and so on, so on. But what we wanted to do was take a step further and develop a spec for the functional annotation, because we didn't want to only limit the source that we have as much as we want to continue developing that source, but there's a lot of overhead in terms of manual curation. We wanted to use our collaboration with the PHAGE, which is Public Health Alliance of Genomic Epidemiology. In case you don't know, this is, there's a data structures group which works on defining these specs. So we are working with them to develop these specs based on the AMR detection and use that for anyone who would like to overlay their own functional annotation on top of the heat map. That's where we're going with. So this spec will be released soon, and this will be available along with the tool itself. So this will allow all kinds of different functional annotations, including the viral drug resistance data or antibody data, and anything that you would like to overlay, as long as the format is used. Okay, now comes this genomics workflow. So we started with some of these components, pre-processing, quality control, variant calling. I'm not going to go into the details of the tools. I'm sure everyone is familiar with these tools. Most of these are available through NF Core. So I've been using those, and if not, then we developed some tools, including some of those custom modules that require integration of contextual data. I think that has been the key, first of all, the challenge, and also something that we've been working on to make the Nextflow modules that can take the contextual information and the genomic information and merge them together. So once you've got this pre-processing, quality control, and variant calling, you come to this VCF file, which can then go into our 3 main annotation sub-workflows: the contextual annotation, the mutation annotation, and then the surveillance reports. So we generate 2 kinds of surveillance reports, one for the machine-readable, more JSON structure, and TSV files, and then also a PDF-based summarized surveillance report, which is much more for the public health folks. So that's where our collaboration with public health has been really helpful. So essentially, you have another entry point where if you want to skip the whole QC and variant calling, and you have a VCF files, then you can just use that VCF file and get the annotation. Now, the structure of surveillance reports, we've got 2 kind of main components. The first one is the indicator. So this is where our collaboration with the FAC, Public Health Agency, helped us to find out these indicators that they look for example, the infection severity or the vaccines or the monoclonal antibodies, and then subgroup our functional categories that we had in our annotation into those indicators, and then list out all the mutations that we see in a certain population, in a jurisdiction, in a time frame, and then see these are the mutations that are linked to these functions and the indicators. And then go into a detail of each specific mutations. That's where you can see the mutation, what subcategory they are from, which lineages do you see these mutations in, and the citation for the source of evidence and the frequency of that mutation. In order to capture all this data, we went with the structure called genome variant file, GVF file, and designed a spec which would allow us to capture all this information, including the genomic and on the contextual information. And essentially, we're going to also release all the specs for this, how we are capturing this data, and what kind of key pair values that we are filling up using the genomics analysis workflow. Okay, now back to the topic, which is basically, once we had this system, everything established, now we want to take it a step further. So we wanted to move towards pandemic preparedness, which is moving from COVID MVP to a virus MVP. So first step was, how we wanted to move to data and pathogen agnostic. And this is essentially the choice of, and I'm really thankful that at the time I pushed to use Nextflow at the time, because all these characteristics that we've been hearing for the last 2 days of Nextflow and NF Core, they kind of came quite handy because, for example, the fast prototyping, that helped me to prototype these modules that I was building for this integration of contextual data into genomic data, the reproducibility and the portability, because the idea of building this tool was not at all to just keep it in our lab. We wanted for the public health folks to use it. We wanted everyone to use it. So the idea of this portability really helped to scale up. So now this is an example of how the backend workflow, the way it captures data, we can group differently to become data agnostic. So the same data that we were looking earlier now is grouped into weeks, epi-weeks, rather than the lineages. And this is really important because now you can see the same mutation, R3463, increasing week on week. So this is an example from the end of 2022 to the start of 23, where this XBB 1.5, if you're not familiar, this is a recombinant Omicron subvariant that was really on the rise. And this mutation linked to the ACE2 receptor binding was increasing week on week. So this ability of the workflow to define that we want to group data by time and then have the same specs load up, the visualization is completely agnostic to what kind of grouping is done. And this allows you to see specific mutations week on week. But this was not enough, so we wanted to add one more component, because we've seen that over the last few months and a year probably, a lot of surveillance has focused towards wastewater surveillance now. So we're going towards the environment sampling and looking at the wastewater rather than the clinical sample. So we added another component which was specifically for the wastewater. So now you can process the wastewater data and bring the same VCF file into annotation and visualize very similarly. So in this case, your y-axis right here these are the samples, and this is a similarity data to show how it can work, but we've been also using this as a production instance. And then you can also connect with the lineages itself to see the difference between the wastewater sample, which is, as a reminder, it's a mixed lineage sample. So you can see certain mutations in those wastewater data, compare it to the clinical data that you have in lineages. Right, so once we had this lineage group visualization, time-based, and then wastewater as well, so we wanted to move towards pathogen agnostic. So what was initially COVID MVP then turned into virus MVP, and now we started to move towards other viruses as a pandemic preparedness. So instead of one workflow of COVID MVP, now we have three. We started to developing a mpox specific instance, which is a pox MVP, and the next one we're working on is for the influenza, called as flu MVP. So again, in this case, the sub-workflows are expanded, modules expanded. Now we are over 50 modules in this workflow. 3 main workflows using a plug-and-play approach. We've heard this term a lot in the last couple of days. We still want to do that as all the modules be a part of puzzles, and then the overarching workflows can connect them into a logic that works for that specific virus. So this is an example of how quickly we can spin off into different viruses. So we challenged ourselves to create this visualization for create this data specifically for the pox MVP, and in this case, this data again used from the ENA. Same genomics workflow with the different specs can be loaded up into similar visualization. And now we're working towards the curation of functions for mpox and then taking it further to the flu. So now the question is how to set up this whole 3 independent components. So what we wanted to achieve was link all these structures with a common file, which is the JSON file that holds all the key for the visualization part, for the genomic analysis, and also for the functional annotation. So what we did was essentially create a JSON file from the GFF file that you get from the NCBI for each, based on the NCBI taxon, in this case the SARS-CoV-2 and mpox, and hold all this information, including the different genes and proteins, and what colors are. It's slightly difficult to probably see here, but information about the protein and the starting point, end points of each protein, the colors that we want to add to the bar. So everything is captured in this JSON file. And this JSON file is connecting all 3 components together. And the workflow has a smaller sub-workflow called configure virus MVP, and that basically generates this JSON file based on the NCBI taxon provided. So in summary, this virus MVP is an interactive framework to process and visualize pathogen and data agnostic mutations, to overlay the functional annotation that we are creating or any other functional annotation based on the specs that we are developing, and then analyze both the clinical or the environmental samples in wastewater form. And you can also group the data by different variables, including the lineage, time, region, and see and explore the same data by different perspectives. The backend genomics workflow is also integrated and containerized, which allows uploading the sequences to the front-end visualization and processing on the go, so that you can see your new sequences added to the same library that you have already built. And there's an option to download the surveillance reports, as I mentioned earlier. So lastly, I would like to talk about this deployment and dissemination. So what we have done so far, so we have a COVID MVP instance that is running, and it's been integrated into the national surveillance ecosystem in Canada for the SARS-CoV-2. It's an end-to-end automated instance. We've done cron jobs to take data from the VirusSeq data portal, which is the national data portal for sharing the viral data. Currently, it holds SARS-CoV-2 data only. So twice a week, we process 500,000 genomes and produce this visualization on the production instance. It's completely automated. The second part is the POX MVP, which is also running currently on GISAID data only for research purpose in our own group, those people who have this access to the GISAID. That's a Cameo group. And then the last part is the flu MVP, which is under development, because the idea is that as much as we want to develop this generic visualization and as much as we want to develop generic workflows, we also want to make sure that the characteristics of viruses are not lost. So we want to develop a additional plugin or additional way of visualizing flu, which is a segmented genome as compared to the SARS-CoV-2. So we are going to visualize segments by segments. This is currently under development. You can see a preprint on the QR code. We're hopeful to submit the full manuscript soon. And then there's another ISID presented this at the conference that last year that gives a bit of a perspective on how this can be used into a more general surveillance system. And with that, thank you very much, and I'm happy to take questions.
Excellent. So I'm not seeing any questions quite yet in the Slack channel, though I do see a little bit of typing. So if there is a question, now is a great time. Well, I think we could probably keep that going in Slack. I don't want to keep people from the coffee break. And I'm sure that you'll be around to answer questions if anyone here has them. But give it up one more time for Zahib. Excellent. And with that, we have a half an hour, I think, coffee break. So feel free to grab some coffee. And again, we've got T-shirts, we've got stickers, and the hashtag, if you want to do any posting, is Nextflow Summit. Thanks again, folks, and see you in half an hour.
Oh baby, I wanted you to be here inside my arms where the night goes down. Oh baby, I wanted you to be here when the sun comes up and the day goes by. Oh baby, I wanted you to be here inside my arms where the night goes down. Oh baby, I wanted you to be here when the sun comes up and the day goes by.
We should be getting started in about a couple minutes. So grab your socks, whatever else at the table, last coffee, 2-minute warning. All right, looks like we've got everybody back. Hope everyone's refreshed and ready. This is our last session. Save the best for last, hopefully. I'd like to introduce Anne, who will be talking about contributing to the NF Core today.
Thanks, everyone. Thanks for having me and for all the great talks so far. So I'm going to talk a little bit about NF Core pipeline in a client project and some of the synergies involved in that. But first, I'm going to talk a little bit about who we are. So I'm part of CS, and it's a global professional services company. And in that, we have an R&D team that works closely with R&D in pharma and large biotechs. And I'm part of CS Discovery, where we work specifically with early R&D, helping the clients improve their R&D capabilities and successes for target discovery, data and knowledge management. And some of the projects that we're working with are drug discovery, target discovery, precision medicine, research strategy and transformation, and then what's probably most relevant for today is the data and knowledge management part of it. So we're part of a global organization. I'm based in Copenhagen, and globally in CS Discovery we have, it says 110, I think we're actually more about 140 at this point, and we are scientists with like many different backgrounds, lots of bioinformatician, engineers, doctors, software developers, and we do still publish together with clients, but also as part of academic partnerships that we are part of, and this is to stay connected to the science and innovation that's going on, and what we also do in order to facilitate this wide range of projects that we're doing with clients. We're bringing additional expertise through different partnerships, and a good example of that is a partnership with Seqera, which is allowing us to more seamlessly implement end-to-end Nextflow solutions for our clients. And that brings me to our use case. So we have an example here of a collaboration between CS and Boehringer Ingelheim, where we worked together on a project, and Boehringer Ingelheim wanted to more seamlessly run their single-cell analysis. They had already decided on using the NF-core single-cell pipeline for obvious reasons. It had a lot of functionalities that they needed, and they saw the benefits of the community and the definitions of the best practices that the NF-core pipeline would ensure. So that was already a good step in the right direction. And the NF-core pipeline does a great job, but there are different scenarios in different institutions, and there will always be custom needs. So when we're working with proprietary or personal sensitive data, you cannot necessarily use all, like, the processes of retrieving data from the NF-core pipelines, and there will be different databases internally that it would need to communicate with. They might also have like some specific customized need for the pipeline itself, and then additionally there can be downstream processes or sending the data to internal customized databases or apps. So they did this in 3 manual steps, but they wanted to run the pipeline on the Seqera platform. And at this point, they could run step number 2, but it was difficult to run everything, and therefore it was not so easy to scale it up or productionize it. So that's where we came in. So for the production, this needed to be transformed into one single process containing these 3 different steps. So interacting directly with their internal databases, running then a customized version of the NF-core pipeline with some additional analyses, and then uploading the results. And this allowed the users to only interact with the pipeline once when they needed to analyze a data set, which means that they could run everything on the Seqera platform, and additionally, they could instead focus their time on looking at the data and the results that came out of the pipeline. So, and this brings us to one of the main points of how was this actually possible. And here, it was the combination of having like the guidelines and the requirements of having an NF-core pipeline, that you know how it's set up. Even if it's updated, you know that it adheres to a specific structure. And together with the modularization that was introduced in DSL2, we could do this combination of the NF-core pipeline together with custom adjustments. So basically, the different steps of the pipelines are retrieved from the different modules, and they can be from NF-core, or they can be local, or from somewhere else. It doesn't really matter to the pipeline. You just retrieve them, and therefore you can as you need to, and customize it. So this also means that if there is an update or a bug fix in one of the modules, you can create a merge request, in theory, without conflicts. That's a very theoretical scenario. Of course, there will be no There will always be conflicts, but this way that you can actually see and track where it's going on, and it's actually manageable. So that's makes things a lot easier. So this is like really good for the client. It was really good for us, but is it also actually good for the open source community, or are we just leeching off of other people's work? I of course say no. We absolutely don't. So before this project, no one from CS had ever contributed to the single cell pipeline in NF Core, and now CS and employees and BI people are actually among the top contributors to the pipeline. So of course, if there's a bug fix that needs to be done and we're working on the pipeline, we're going to fix it for everyone. It doesn't make sense to only fix it in a local version if we're using a standard module from the pipeline. And this means that the development can happen faster because there's suddenly a company that has an incentive to make it happen, and it's not something that someone has to do off their in their spare time. Yeah, so I would say that this is a very beneficial thing for both the open source community as well as pharma and biotech companies to benefit from this and be able to have even more people testing it and defining the best practices for how to use it both in an academic research setting as well as in a corporate research setting. So in summary for that, like pharma companies should not be afraid of using these. You'll always have customizations and you'll always do things maybe a little bit differently, but it's all in all a very big benefit to be able to use this together with a large community that supports it. So with that, I will very much like to thank the team at Boehringer Ingelheim for the collaboration and for allowing us to talk about it here, and our colleagues at CS Discovery, especially Felipe, who was the one actually doing the work, and then our people at Seqera for working with us on various issues and challenges, and of course the NF Core people behind the NF Core and the community as a whole. So thank you very much, and yeah, take any questions.
Thank you so much, Anne. It's so great to see the commercial and the industry actually contributing back to the open source, and thanks for spearheading that. We have a question here. Do you plan to work on any of the other NF Core pipelines?
That's a good question. Yes, we do. We do definitely. I think from our part, there's both an aspect of having someone, having our team do it for the practice of it. Like we're expanding our team a great deal, and that also means that there's a lot of people who need to learn. So contributing to the NF Core pipelines will be a good way of actually learning that and learning some of the best practices. And then we also do have plans to contribute in other settings, but I don't think I can reveal at this point which pipelines.
Okay, well, there's a suggestion here from Maxime about Sarek, if you'd like to contribute.
Yes.
And then another question just came through. How do you manage client-specific requests and NF Core community general needs, and how do you, if conflicts develop or when you develop a pipeline, how do you prioritize that?
Yeah, that's a good question. I think I'm not the best person to answer that, but in general, I mean, it will always be a balance, and sometimes it can be obvious that this is something that everyone can benefit from. In other cases, it will be clear that is something that's a very specific case. And then there'll be a lot of gray areas. And in that sense, it would usually be up to the client to be able to determine that.
Okay, well, great. Thank you so much. I don't see any more questions coming through. Let's give it up for Anne again. Thank you. Next up is Harshal. He's going to talk to us much anticipatedly about the automation on the Seqera platform, as was hinted in a couple of other talks.
Great, thank you. It's awesome to finally have this event on this side of the world. I know that there's been some heavy Nextflow users, NF Core users on this side of the planet, and we've not really been able to get here and make the reach. But I think probably this is the first of many to come, and it's just amazing being here and just seeing the vibe and the community that we've got going on here. So before my last talk at the summit, I set up some audience participation where I asked the audience to correct me whenever I said tower instead of Seqera platform. That was mostly for my benefit. It backfired horrendously because I just got random people in the street coming up to me and saying it's Seqera platform. And it's never been the same since. So feel free to correct me, but just be nice. So what I want to talk to you about today is automation on the platform. So Evan gave you a brief overview of the features and give you a quick stop tour of the platform. But us as a team, the scientific development team, which I head up at Seqera, we're very much interested in doing what normal bioinformaticians do. Automation, writing tools, scripting, writing pipelines. We still contribute a lot back to NF Core. I myself have partially been responsible or maintained or written 8 NF Core pipelines, including the RNA-seq one, FetchNGS, ViralRecon, which was written in the pandemic. And it's just an awesome community, and it's just growing and getting better and better. So us as a team, we do various different things. Our primary role is really to make our customers successful. And so we'll interact with our customers and give them what they need, the support, whether that's helping with issues on the platform or pipeline development and that sort of thing. We also are very, as I said, heavily involved in still contributing back to the community. So our team is still also driving the evolution of the platform and the standards, as well as what happens on NF Core and how we can push the boundaries with Nextflow as well to improve pipelines on NF Core. So those best practices are continually evolving as things change. So Seqera platform itself, there are various features. I won't go into each one of those. There's cloud expenses and various other things that you can benefit from by using the platform. But as I said, I want to talk to you more about the automation aspects and how you can achieve some of these things. And so to break it down, I guess there's 3 types of approaches, 3 types of users in terms of how you may want to use any tool, really. Is you have a UI type use case where you want to launch a pipeline on a platform by clicking some buttons. And so that's a typical sort of wet lab biologist type user. You can have API submission of tasks and jobs or launching pipelines, and that would be more of sort of, if you've got existing systems that you want to hook in via API calls and leverage API automation, you can do it that way. Bioinformaticians in general love CLI tools. We love CLI tools, and they're just easy to develop on the command line, to install, to update, and to do all of these things in a nice sort of consistent type of way. Users don't necessarily fall into any one of these buckets. Users typically span the spectrum, right? So, I might want to today just click a button and launch a pipeline on the platform because it's just there. And I don't want to have to use a command line tool. It's a convenience thing. For something else that I'm doing repetitively and I don't want to get carpal tunnel, I might use a CLI, for example. And so it really depends what you want to do. I guess the key sort of take home, I want to emphasize is just having the flexibility for bioinformaticians is very important. I know that. I've done it. I've been there. And it's just nice having the option. So this is the typical launching via the platform. You click a button. Evan showed you how to do that earlier. You add a data set, and then you launch a pipeline. You can use API calls, and in this case, we're just posting a request via Python via the Seqera API to, in this case, launch a pipeline on the platform. You can even use the CLI as well. So we've got a command line interface, which allows you to essentially simplify how you interact with the platform. And so I guess in order to understand how these all work on the platform, you sort of need to understand the core components. And so the way that the platform is typically structured is you have three main components. You have a backend database that stores all of your metrics. So anything that you see in the user interface is stored in a database. Whether that's run information, user information, all of these things are stored in that database. Then you've got a backend container that is essentially making API calls between the database and the front-end container. And the front-end container is what puts the application up in the UI. And so all of this is actually all being done by API calls behind the scenes. And what the CLI is essentially built on top of the API. But it's more convenient to use because when you want to launch a pipeline, you might have to have 3 API requests, right? And rather than having 3 API requests, the CLI hides all of that behind the scenes and just says Seqera launch RNA-seq. And so those particular API requests are already chained behind the scenes for you, and you use a CLI interface, which is much neater. What's also nice about some of this is that with the CLI, you can even import and export entities in the platform directly as code. And so you may want to store how you created something in the platform. It's all well and good, happy clicking buttons, creating stuff, but you want to be able to reproduce what you've done and have infrastructure as code as well, potentially, if you want to maybe spin up the same compute environment again in a separate workspace or add another pipeline in a different workspace for another reason. And so being able to export that as code is very powerful because you can store it, you can version control it, and now you're essentially not only version controlling your workflows, but you're also version controlling how you've created everything in that environment. So what we've also developed as a team is a tool called Seqera Kit. So you've got the API. The CLI is built on the API, and Seqera Kit is essentially a wrapper around the CLI. And so all of the typical options that you'd get exposed when you run on the CLI are exposed in a very nice standard YAML format. So on the left here, you can see when you want to launch a pipeline, you can essentially define everything in YAML format. You don't need to interact with JSON or anything like that. Any CLI options are available within this YAML format for you to then leverage for your own automation. It's much easier to maintain, it's much easier to update, it's much easier to store and understand. And so given the fact that this tool has been written in Python, another aspect is actually the ability to then not only launch via a simple YAML file, but you can import Seqera Kit within the context of a Python script and then exploit the capabilities of the CLI directly from within Python 2. So there may be use cases where you want to do some more dynamic things that you can't really define in an end-to-end YAML format. And so you might want to do things in between processes or maybe adding data sets, automation, various other things. And being able to import the Seqera Kit and the CLI functionality within Python really opens up the possibilities of automating your processes. So, in true Seqera style, I'm going to try and give you a live demo now of how some of this looks. So just so you know, key.io was down half an hour ago, and I'm hoping that it isn't, so please cross everything for me here. Right, so I've just opened up a VS Code editor, and here I'm going to do a couple of admin things, and it will all make sense a bit later on, so just bear with me. So I'm just running a simple server here. I've got a Python script in this folder that it's like 40 lines of code that runs a server. And I'm going to open a port in this terminal. I'm going to copy this. put it in this Nextflow config file. And so what I'm doing here is essentially setting up a server where I can post requests and listen to events that are coming in via this weblog functionality that there is available in Nextflow. This might be deprecated, so don't take this seriously. I just wanted to show you how this could potentially work, given mostly because we were asked questions about chaining pipelines together, and I thought I'd put something together. Okay, so Seqera Kit. Right, so when you want to create entities in the platform, you can define anything that are variable, like an organization name or a workspace name or a team or the members you have in that team, the name of your compute environment, which region you're running in. These things are things typically you want to change potentially when you're creating new entities in the platform. And so what you can do is you can have a simple bash file like this that is essentially just exporting a bunch of variables within the executing environment where you're running this tool. And so what I'm going to do is I'm going to source this file. And so now if I just take any one of those variables, they should be available in my environment, right? The reason this is important is because with Seqera Kit, what you can do is you can create a YAML file where these environment variables are resolved at runtime. And so you create a YAML file which essentially acts as a template for what you want to create in the platform, and you keep the environment variables separate. And so that way, anything that you're likely to change, or if you want to put up another workspace with some different users or whatever it is, you can encode all of that as environment variables, the things you'd like to change, and have other portions of it templated off and are potentially a bit more generic. And so at runtime, what happens is, I've got this YAML file now. I want to create a brand new organization in the platform. I want to add a team. I want to add some members to that team. I want to add a brand new workspace. I want to add some participants to that workspace. I want to add credentials for GitHub, Docker Hub, AWS. At the bottom here, I'm sourcing a separate secrets file, which isn't visible and not recorded. So that's where those are coming from. And so here, I'm creating a compute environment on AWS Batch. I'm using the batch forge mechanism that we've got on the platform, which is really powerful because it just means you can go away and create all of the resources you need to run your compute in a very easy, standardized way and not have to worry about doing this manually within your own AWS account via a console. I'm also going to be using Fargate here as well, and that just means the pipeline should spin up and start running very quickly. And I want to add a Hello World pipeline and test it. And so this is an end-to-end flow going all the way from creating an organization, adding members to that organization, and filling it out with everything that I need to be able to run a pipeline. And so I can just do all the things. And so what should happen is this tool now picks up all of this configuration. Behind the scenes, it's just calling the Tower CLI. You can see the commands printed here. And so it will go through in order, create what it needs to. At this point, it's stalled a little bit because we now need to create the AWS compute environment in the platform. So if we refresh this page, you see there's a brand new Seqera Kit organization here. I'm just going to bump Adam and Isha to owner status. So if anything breaks, I can point the finger at them. And so this is still creating. So if we look in the workspace now, you can see that this is creating. So this will become available in a second. There we go. And then the next step is adding the Hello World pipeline that I showed you. So if I refresh here, we've now added the pipeline. And we've submitted the pipeline. So all of this has been done in less than a minute, right? You can use this however you want. You can compartmentalize it. You can modularize it. It's essentially a really nice, easy way of spinning up anything you want in the platform via automation and storing it as sort of pseudocode, let's say, because it's in YAML format. So now I want to take it a step further. I've got a smaller YAML file where I want to add the data set that Evan showed you in his demo via command line, right? So I've got a sample sheet here, which is simply just the same IDs that he found and used. And what I want to do is take that and, where are we? Yeah, take that file, right, which is this, and then create a data set via the command line in the platform, and add the pipeline also to the launchpad for me to use. And you can see here I'm setting some parameters as well. So when he was going through his demo, he set the NF-core pipeline to, he set the fetch-NGS pipeline to output a sample sheet that could run with RNA-seq. And so all of this stuff you can encode also in this YAML. So all we do is we run the other one. Right. So now we should have a data set here. We've also got another pipeline here. Let's launch this. From the user interface. There we go. So now that's been submitted from the user interface. The Hello World pipeline that we submitted via the YAML is now working. And just to finish off, I want to show you how we can use the Python import functionality that I mentioned in a more dynamic way. So what we've set up here is, and the reason I added that server at the beginning is because what we wanted to do is have the ability to run a Hello World pipeline and then automatically run a fetch-NGS pipeline. Whenever that pipeline completes, there'll be a post request to the server that I set up that suggests that the pipeline succeeded, and hopefully it should trigger the fetch-NGS pipeline after that. And so that's all this script is doing really. It's providing some parameters to run fetch-NGS. It's getting the dataset ID that we've just added, and it should hopefully run the pipeline, he says. So okay, so we should start seeing some server requests here. There we go. And then we've got a brand new pipeline here. The hope is that when this finishes, the succeeded status via the post request will then ping the script then to go and submit fetch-NGS directly after this as a very simple example of how to chain pipelines via automation. Another thing I wanted to show you since the last summit, we'll come back to that because that will take a couple of seconds to kick off. Another thing I wanted to show you is since the last summit also, we've been building out a pipeline. So I've written a pipeline called NF Aggregate, which essentially allows you to run information from the platform, and essentially all you really need is this very simple sample sheet that is your run ID, and the run ID you can get within the UI, for example, from here, as well as a showcase, a workspace as an input, and it will automatically run the Tower CLI behind the scenes and then dump the JSON files and scrape those. And so we've actually even added a MultiQC module for this, natively to MultiQC, and Vlad helped out a lot with that, adding that there. And there's nothing really better to render these sorts of metrics across runs than MultiQC. And so just to show you a quick example while that kicks off. So they're all starting to run now, which is great. Let's switch to another workspace. So MultiQC report is produced as a report. If I download it, open it up. There's also now native functionality for this, anything that's dumped there by the Seqera CLI to be rendered as a report. And this can be really useful if you're benchmarking your own runs or doing various other stuff rather than copying and pasting out the user interface. It just makes it a lot easier and more standardized to share the results and resource requests and requirements and various other things by using something like this as a MultiQC module. So this is something that actually we said we would do at the end of the summit, but also is something now, I guess, to tag on the CLI and automation conversation. It's another thing that we've added now at the end of the Seqera CLI. Okay, so just to finish off, those pipelines are now running. I really want to see that other one get submitted. Still posting away. But to also emphasize how easy this is, Isha has also run exactly the same scripts, and now we are running Hello World in this brand new organization that I've just created. She's running Hello World on GCP, and it's just finished. Adam, who's in the UK, has done exactly the same thing with Azure, and the pipeline is now running on Azure. Again, this just shows you how easy it is to do this once you have something in place and templated together. So now, within the space of 20 minutes, we've set up an end-to-end environment where we can start running Nextflow pipelines and hand it off to users for their own benefit to start running these pipelines themselves. Okay, I'll leave this running in the background. But yeah, that's it from me. Thank you for listening, and happy to take any questions.
Anybody has any questions while we're waiting for the pipeline to finish? Not seeing much here in the Slack. All right.
I can't access Slack, but I can check from you. Is it possible to export a whole workspace with all of that you already defined?
That's an excellent question. So I should say that Seqera Kit is in beta. We use it every day for everything. So any feature requests, bug fixes, we're very open to improving it. The short answer is we've started working on it. So what would be awesome actually is okay, this is sort of a one-way thing where you can go and create everything. A lot of this is actually been implemented by Isha, and what she's also added is the ability to delete these resources in order as well. So say, for example, you want to spin down an organization, you can just do a -- delete and delete everything too. But what would be even better is the ability to essentially manage infrastructure as code and automatically be able to have diffs over time as to how things change, right? So if your YAML template is what it looks like today, then maybe having the option of some sort of dump or export function that allows you to automatically see what's been changed in that workspace over time. So we're trying to figure out how to implement that, yeah, hopefully soon. Yeah.
Thank you, Harshal. I guess we don't have...
Well, we do. Look, it's been
submitted.
There we go. Look, there we go. So the post request probably came in. There we go. The stress this caused.
Now that's a perfect finish to our demo. Next up, we have Ernst, who has already asked for you to prepare your questions in Slack. So while you're listening, start thinking about your questions now, and he's going to be talking to us about Quilt.
Correctly? Great. My name is Ray Prabhakar. I am the director of product at Quilt. I know it's very late. You're ready to go to sleep or go drinking, but I have to stand over here so that you can see me on the camera. Okay. Hopefully the rest of you can see me as well. So at Quilt, we're on a mission to really try and accelerate scientific innovation by helping teams work together. And let's see if I can get the slide here. It'll take a little while to render. How many of you spend your time mostly working with software? Just out of curiosity. Okay. How many of you spend most of your time working with hardware or like physical instruments or wet biology? One brave soul in the back, thank you. How many of you spend your time actually working with people? Very reluctant hands going up, I noticed. So I've been in the technology world for a long time. I was at Apple for 17 years running open source. I was a physicist before that. Like most physicists, I spend my time running cables for biologists now. And one thing that I've discovered is human problems are the hardest and the most interesting. And if you can actually understand those, the science, the impact, and the funding becomes much easier. So at Quilt, we sit at the intersection between all these massively complex data systems and the businesses and the people that you need in order to, one, get your job done, and B, have a meaningful, fulfilling life on occasion. And so what we do is we build a series of tools that help you get this amazing data that you're building with your Nextflow pipelines and other places into the rest of your organization and your outside consumers, so you can help them see what you are doing and be part of collaborating with you on those new things. So the main product that we sell is a thing called the Quilt Catalog, which is a way to act as a sort of front door for Amazon S3. And the reason it's interesting in this context is we have a wonderful tool that we introduced last year called NF Quilt. So if you run a Nextflow pipeline, a lot of new people here, it's amazing what you can get. And then you run the pipeline, and then you get a line on a page, which is nice, but not terribly exciting. It's not the sort of thing you can show to your mother or even to your colleagues. And so what we've done is we've created this plugin last year, and we just released it a month ago as a pure Java solution, directly native inside of Nextflow, where all you have to do is there's one little command where you've been doing a S3 URI. Currently, we only run on Amazon, though we're looking at adding back-end support for other systems. And you give it a Quilt plus URI with this idea of a package. And a package is a flexible, interoperable data container that is sort of a way to freeze dry all of your work with its metadata, its lineage, its provenance, with checksums, so you know exactly this data is available anywhere you take it throughout your ecosystem. And what we can do with that is we actually will go ahead and turn that into a data product so that when you generate your run, it doesn't just grab all the data, it puts it in a folder, it puts it in a package, it adds a checksum with timestamps and versioning, so you know every set of data exactly when it was created and that it hasn't been changed, nobody overwrote it in the box file. And then we pull all the metadata from Nextflow into the pipelines and into the package. And so you can see exactly every parameter that was set when you created the package, the command line, timestamps, et cetera. And we do this beautiful auto packaging. So we will go through and find your markdown files, your text files, PDFs. We can render PowerPoints like I showed in the first slide. And most importantly for a lot of us, the multi-QC file. So directly from the day that you get, the moment you finish your run, it writes it out automatically with all of this visualization baked in, and it gives you a URL that you can share within your organization. And this is all available for free as part of the Nextflow platform. You just do one additional configuration step to add the NF Quilt plugin. And from there, it just works. And we're looking at creating some templates and other forms to make that even easier going down the road. One of the really nice things about this URL feature is that it works with any system. So we have a packager that we released a couple months ago called the Benchling Auto Packager. How many people here use Benchling or some similar limbs in your organization? And one of the things that we found is that Benchling is really great for the scientist who's facing there and talking to the machine, but when they have a lot of data or they need to work with the rest of the organization, it gets quite challenging. So we created an auto packager. I can maybe do a quick demo here. I know that's a little dangerous in real time, but may as well. See what we can pull off here. You have to choose a schema. So we have this idea of a quiltable schema with different properties. But when we set that up there, it creates an entry, and then we use the event-based system, very similar to what they were talking about with Kafka. We use the event bus there. We should see if we can work with some of the stuff that they're doing there for dynamic event-based integrations. And it goes ahead and creates a Quilt package and then sets the information back to actually, I think I may have chosen, yeah, there it is. And so you can see here, right from the day one, you get the Quilt package linked directly to the Benchling notebook. And one thing that I wasn't quite able to finish before the talk today was a version to do the same thing with Nextflow pipeline. So when Nextflow pipeline runs, it'll also grab the URL and push that into the Benchling package. So the idea is that you can have your scientists, your administrators, or your auditors, or your customers with appropriate permissions. We take care of all the SSO and integration with your Okta or your Active Directory, so that only people who are supposed to are able to go through the website and see the documentation, but it's all there. Anyway, I think I got about 3 minutes left, so I have one last thing to show you. So we have this web application, which we've been using for a long time. We have a command line tool that you can use with your scripts. We have a Python API that you can use from your Jupyter notebooks or for your automation workflows. But one of the things we've always been challenging with is that some people, who are, especially a lot of our wet scientists, use very complicated desktop applications like Excel in order to be able to read and write their data. And then it becomes this data sink where data leaves the cloud, leaves the ecosystem, and goes away, and you never see it again. And so we've been trying to solve that, and I won't claim that we've solved the problem completely, but we've taken some interesting first steps. And this is a new feature. This is a pre-release build. It's not available on the shipping version of Quilt yet, but it's called Open in Desktop. So we'll see if the demo gods are with me. And this is because I have the wrong bucket. But no, that is actually my fault because I hacked around something. And I think if I run this again, it'll work. Let's see if this goes. Nope. Let's try one last. That's right, because I didn't click the application. That's what's messing it up. Let's try it one more time. And nope, all right, third time's the fail. So apologize for that. See me, I'm sure once the demo is finished and I go off the stage, it'll work perfectly. We'll have to show you later, but the goal is to make it as easy as possible to take all the hard work you're doing, both as individuals, as teams, as organizations, and as an ecosystem, and provide the tools and the visualizations and the authentication and the security and frankly the joy, so that the data that you're doing will not just be doing technical work to solve technical problems, but be doing human work to solve human problems, saving lives, improving ecosystems, and really building the kind of innovation that all of us got into this business to start with. So thank you very much, and I'm happy to take any questions.
Thank you so much. The demo gods were almost with you. I see a lot of people typing in there. Anybody has specific questions?
They're probably making dinner plans, but.
I'll give it one more minute. Anyone? All right, maybe they'll catch you afterwards. But thank you so much. Let's give it up again.
All right, thank you.
Next up, we have Geraldine, who will update us on everything that's been going on in Hackathon. Super excited to hear about it. Hi, everyone. I realize that I'm one of the last talks that stands between you and getting out of here. But I hope you're having a great afternoon, an early evening. It's terrible that it's already so dark. But there you go. It's not nighttime yet. It's still afternoon, so please stay with us for a little bit longer. Just me, and then Evan will conclude. What I wanted to do here is give you a little summary, a little overview of the NF Core Hackathon that took place for the first 2 days this week. So that would be Tuesday and Wednesday. Time kind of blurs together when you have one of these events. But the hackathon was a day and a half of getting together with people in the community to hack together on various projects. And so what I want to do is not give you like a comprehensive list of everything that got done, because a lot got done, but kind of give you a sense of the flavor of the kind of things we do at hackathons, and hopefully make you want to join us for the next one.
All right, so a group of about 50 people got together. There were 40 people from the community at large and 10 people from Seqera, including myself, of course. And basically the way we organize these, we kind of self-organize into a few groups. In this case, we had 5 different themed groups. It's not like a hackathon where there's a contest or any kind of pressure, anything like that. The idea is really to just get together and work together and also socialize. So we organized around 4 technical themes for this one, plus a meta group of beginners, and each one is kind of led by 1 or more people from kind of the NF core community. And so I'm going to walk you through kind of what each group worked on. My group, the beginners group, I want to qualify, when I say beginners, we had a handful of people. Most of them were already quite proficient with Nextflow. They'd been working with Nextflow for some of them for a few years, but they were new to NF Core. And one of the major themes that kind of emerged there of what people wanted to do was get to understand better what the NF Core resources are and how to integrate them into their own work. Especially NF Core pipeline templates, which garner a lot of interest, but are not necessarily easy to get to work with on first approach. There's a bit of gaps in documentation and things like that. So one of the things we did was just kind of figure out what the gaps are and the kind of things that we need to work on together to make those resources even more useful and widely used. Some people did do actual work in the sense that we have a few people who worked through some training materials and tested features to see kind of what the expected behaviors are. A couple of people actually worked on a new module and submitted a pull request for a new module, which I think is really cool. We had one person who was, 1 or 2, who were complete beginners in the sense of had not worked with Nextflow before, and there it's like, just setting up your laptop and getting to know the tooling and stuff like that. So what I'm really happy about is that by the end of the day, all of them felt comfortable joining one of the other groups for the next day. And so on the next day, I didn't have to lead a group, which was great. But it was really cool to see that they effectively joined the community in working on NF Core resources. So well done to all of them. I'm very proud. Okay, so second group I want to talk about briefly is the NF test group. So if you're not familiar with NF test, or you've heard about it a bunch of times already, but just in case, it is a testing framework for Nextflow pipelines. It's developed by an independent group, but it's really neat and it makes it really easy to have robust testing of Nextflow modules and pipelines. It's not specific to NF Core, but there is an effort going on within NF Core to apply NF test to modules and pipelines that are stewarded by the NF Core community. And so this group worked on just taking existing pipelines and adding NF tests to them. And so I think within the course of the hackathon, they got 15 done, and that gets us to over half of the pipelines in NF Core are now have NF test, use NF test for the testing, which is really good. And we look forward to continuing that work kind of on an ongoing basis. Pipelines, the pipelines group, again, I'm not going to give you a full breakdown, but they're up kind of for your information. The kinds of things people did in the pipelines group, one is just talk about some pipelines that have been proposed and kind of get a sense of what the interest is, who would work on them, and so on, what they would look like. Some people got together to work on existing pipelines, works in progress that are in various stages, including things like trying to get it to work, making it NF Core compatible, things like that, continuous improvements. There's kind of a variety of things that you can do. And this kind of reflects the variety of work that's in progress right now. Also, it's definitely a constant theme, is adding tests to existing pipelines. So you'll see there's overlaps in the concerns between the groups. Adding more tests to more pipelines. A few people also did some work on custom pipelines that are not part of the NF Core corpus, but utilize some of those NF Core resources, best practices, and so on. Modules. Modules are components of pipelines, of workflows. You can think of them, a single module is typically a wrapper around a single process. And the idea is to have a library of modules, a library of tools that are commonly used in the community, so that if, let's say, I'm developing my own pipeline and I want to stick, let's say, GATK haplotype caller in there, I don't have to write a new module. I can just use one that exists. Of course, you might tell me, if I'm making a pipeline with haplotype caller, why am I not just using Sarek? I don't know where Maxime is, but yeah, that's the kind of thing that it's for, right? And there's a bunch of new modules that got added, which is always great. Again, a subset of people took existing modules and added NF tests to them. I'm not sure if we're double counting or if that was just done independently. I should caveat that the content for these slides is largely crowdsourced by the groups themselves. I take no responsibility whatsoever, maybe a little bit, but none for the GIFs. I will take responsibility for saying GIF and not GIF, though. It's a very strong opinion there. All right, another thing that got done, somebody added a new sub-workflow. If you're not familiar with that, a sub-workflow is like something intermediate in between a module and a workflow. So it's like a piece of workflow that can be used kind of in a modular way, but it's more than just a module. The definitions are a little bit fuzzy for kind of obvious reasons, but it's a piece of workflow, let's say. And new test data. Can't have tests without test data. So adding new test data is always a very useful thing. The ops team, self-described, they told me to spell it this way. This is a team whose efforts aim to automate a lot of the things that need to happen in terms of, NF Core has multiple resources. There's Slack, there's GitHub, there's websites that is built from GitHub. There's a number of infrastructure components, and one of the goals of the team is to get these things to talk to each other and have as much as possible automated and not done manually, with the goal of overall breaking fewer things by accident, which I don't know what that means about their intent to break things on purpose, but at least avoiding the accidents is a good idea. So that's what they're about. I'm a little bit fuzzy on what they did during the hackathon, to be entirely honest. You can ask Edmund, he knows everything. But my understanding is that they didn't break anything, so well done there. Okay, and finally, so that's the work that got done. About halfway through, with the goal of relaxing a bit and socializing a little, we had a quiz. So this is traditional in the NF Core Hackathon. Halfway through, we have a quiz. Hosted on Kahoot, there's a thing you vote. I won the quiz, okay? I won a rubber ducky and a really cool gold sticker for my laptop. I say this because some of you know, I joined Seqera just 5 weeks ago. This is literally week 5 for me being on the job, which is very exciting. It's been a bit of a whirlwind. And I joined specifically the week of the Hackathon and Summit in Barcelona. And at the Hackathon in Barcelona, I did the quiz, and I was not dead last, but I was like in the last 5 or something like that, the point where you don't count anymore. And I knew practically nothing. And I had never touched Nextflow before getting hired to Seqera, by the way. I admit it freely, I came from Whittle. I'm learning a lot, it's really great. And what I want to say here is that in just 4.5 weeks, I learned a lot. I learned a huge amount, obviously, since I won. But it's like, part of it is questions about technical stuff. Part of it is questions about the community. And I learned so much because so many people in the community have helped me on board on the technical stuff, helped me kind of understand how this community works. And it's a very active, very dynamic community, and it's just been extremely energizing. And so I just want to say thank you to everybody who has been so helpful so far, because this ducky really is yours. Thank you. And so thank you to everyone who came and participated in the hackathon. Also thank you to everyone who came to the summits. Evan is the one who's going to do the big wrap-up for everything, but I want to say thank you so much for all showing up and being very active and just incredibly welcoming and friendly. Thank you.
Thank you so much, Geraldine. Stay up here for 1 second. We got questions. I really do appreciate that quote of breaking less things by accident. I think I'll take that as a motto in the future. One question for you. What are the whittle chromo features that you think that are missing in the Nextflow?
Oh, how much time do we have? I'm kidding. It's not like there's a lot, but I have a lot to say about like 1 or 2 things. No, there's a few things. We should talk about that another time, maybe over drinks. But there's a few things I think that where workflow language communities can learn from each other, and I look forward to having some interesting conversations. I've already had some really interesting, spirited conversations with some of the members, and I think there's a real willingness to kind of learn from each other and see, because ultimately we're all trying to do the same thing. We're trying to help researchers get their work done faster and with less hassle, and so this is an area where I see it as very much a collaborative effort and not a competition. So anybody who wants to talk about that, I would love to, anytime.
Let's applaud Geraldine again for winning the quiz.
Thank you.
And Evan is up next to close us off.
Very long, folks. But just a couple of thank yous that we want to make these events possible. It does take a lot of work from people, particularly when we've been doing a lot of this remotely or based in Barcelona. So I'd like to thank, first of all, the Seqera marketing team, in particular the events part of that. So Irina and Anna have done a great job of pulling everything together, and congrats to them. Also, you would have seen from Geraldine's talk, there's a lot of work that goes on in the community and our developer advocate team. So Phil has recently kind of moved on from there, but I know that he's still been very active in there. Also, Geraldine, who's recently joined us, and Chris, who's been doing a great work on all the kind of technical parts of that. So thanks to all of you folks as well. And finally, to Justin from Premier Events. So Justin's been able to come in and help us and do a lot of the organization for the event, as well as all the staff from the venue and the technical staff as well. So thanks all to you folks. And finally, so this year was a little bit weird in that we had the Nextflow Summit in Barcelona about a month ago, and then we basically came straight into here. We're not going to do that insanity anymore, basically, and we are going to try and split these events up so that they're a little bit more settled. We're going to then be able to try and bring even more new, exciting things every 6 months as well, and it performs as a very good time to be able to release things and to work towards that. So these dates are to be confirmed, but we're looking for Boston in May, likely mid-May, and the Barcelona event will be in October as it is. So you're all very welcome to join us next time. we'll have more very shortly on the confirmation of those dates. And with that, I'd just like to say thank you to everyone here for your involvement. It's the first time we've done this event. It's been fantastic to get to meet many of you in person for the first time and go around and speak, and looking forward to seeing you in the community. Thank you all. That's us.